Not every ancient mystery was created by what people built. Some were created by what people chose to hide. Across the ancient world, archaeologists have uncovered sealed passageways, buried chambers, intentionally destroyed inscriptions, and entire structures concealed beneath newer civilizations. In some cases, it appears that ancient societies were not trying to preserve their world for the future, but erase parts of it completely. And yet fragments survived. A staircase beneath a collapsed temple, a forbidden tomb hidden behind layers of stone, a city abandoned so suddenly that everyday objects were left untouched. These discoveries reveal a strange reality about the past. History is not only shaped by what survives, but by what was deliberately removed from it. And sometimes the missing pieces become the greatest mystery of all. Southwestern Greece, near the Bay of Navarino. Buried beneath olive-covered hills, the Palace of Nestor preserved evidence of a Bronze Age civilization that may have mastered engineering, administration, and material science far beyond what historians once believed possible. The palace was excavated in 1939 by American archaeologist Carl Blegen after local farmers repeatedly uncovered fragments of pottery and unusual stone blocks near Ano Englianos in Pylos. Beneath the soil, archaeologists discovered one of the best preserved Mycenaean palaces ever found, dating to roughly 1300–1200 BCE. What shocked researchers was not only the scale of the structure, but the advanced infrastructure hidden inside it. Drainage systems, bath chambers, ventilation engineering, archive rooms, industrial storage sectors, and over 1,000 linear B clay tablets containing one of the oldest administrative records in Europe. One of the most disturbing discoveries at the palace was the sheer complexity of its bureaucratic system. More than 1,000 linear B tablets were found scattered across archive rooms, recording inventories of olive oil, bronze, livestock, weapons, textiles, labor assignments, and religious offerings. The records suggest the palace controlled an enormous regional economy stretching across Messenia. What makes this mysterious is the level of organization involved. The palace operated almost like a centralized state ministry nearly 3,200 years ago. Some historians compare its logistical complexity to administrative systems seen in classical Rome more than a millennium later. Tablets recorded exact quantities of bronze allocated to weapon production, the number of workers assigned to specific tasks, and even emergency military preparations possibly connected to an approaching invasion. The tablets themselves were never intended to survive. They were made from sun-dried clay meant for temporary accounting. Yet when the palace burned around 1200 BCE, temperatures inside the fire accidentally baked the tablets into ceramic-like permanence. Ironically, the destruction of the palace became the reason modern historians can study its administration today. Researchers estimate that the kingdom governed from Pylos may have controlled over 50,000 people. For comparison, many European societies of the same period remain decentralized tribal communities without formal writing systems. The existence of such an organized bureaucratic machine during the Late Bronze Age continues to challenge traditional assumptions about the technological limitations of Mycenaean Greece. The palace was built in one of the most seismically dangerous regions of the Mediterranean, yet major portions of its foundations survived for more than 3 millennia. Archaeologists discovered that walls were constructed using combinations of massive stone blocks, timber reinforcements, and softer intermediary materials capable of absorbing vibration. Some engineers believe the Mycenaeans unintentionally created an early form of seismic damping. Several floor layers also appear deliberately distributed to reduce structural stress during tremors. Similar anti-seismic concepts would later appear in parts of Roman architecture and much later in Japanese earthquake-resistant wooden construction. This raises a major question. How did Bronze Age builders develop architectural methods sophisticated enough to survive repeated seismic activity without modern mathematics or structural theory? Evidence suggests the builders may have accumulated generations of empirical engineering knowledge through repeated reconstruction after earthquakes. Yet no surviving text explains the principles they used. The palace appears to represent a lost tradition of practical engineering developed long before formal architectural science existed. Inside the palace, archaeologists uncovered surprisingly advanced hydraulic systems. Terracotta pipes carried water through different sectors of the complex, while drainage channels were built with carefully calculated gradients, allowing water to flow continuously without pumps. Some corridors contained bathing chambers equipped with large clay bathtubs remarkably similar in shape to modern designs. The drainage slopes were engineered so precisely that water runoff remained effective thousands of years later during excavation tests. The central Megaron Hall reveals another technological mystery. At its center stood a circular hearth nearly 4 meters wide surrounded by 4 large columns. Studies of airflow patterns suggest the structure may have created a natural convection system capable of pulling smoke upward while distributing heat evenly throughout the hall. Most Bronze Age interiors became dangerously smoke-filled during prolonged fires. Yet the design of the Palace of Nestor appears unusually efficient. Some researchers believe roof openings and hidden ventilation gaps may have functioned almost like primitive climate control architecture. Comparable passive airflow systems later appeared in Persian wind catchers and Roman bath complexes, but the palace predates many of these innovations by centuries. Among the palace's most baffling discoveries were its frescoes. Even after more than 3,000 years, many sections retained vivid red, black, blue and white pigments with extraordinary color stability. Chemical analysis revealed that Mycenaean artists used finely ground mineral pigments layered onto wet plaster using techniques resembling true fresco methods, later perfected during the Roman and Renaissance periods. The binding between pigment and plaster became so strong that portions survived fire, humidity, burial pressure, and centuries of environmental change. The blue pigments are especially mysterious. Some mineral traces appear linked to materials originating far beyond Messenia, suggesting trade connections extending across the eastern Mediterranean. Certain compounds resemble Egyptian blue, one of the world's earliest synthetic pigments, which required heating silica, copper compounds, calcium, and alkali to temperatures approaching 851,000 degrees Celsius. Producing such pigments consistently would have required controlled furnace temperatures, specialized mineral knowledge, and highly refined preparation methods. Yet, no written Mycenaean text explains how these paints were manufactured. Microscopic studies also show that several wall paintings were applied in multiple ultra-thin layers, producing depth and luminosity rarely associated with Bronze Age art. Some restoration experts compared the durability of the pigments to medieval frescoes that are more than 2,000 years younger. The palace's griffin frescoes, marine imagery, and ceremonial scenes remain among the best-preserved paintings of the late Bronze Age world. Their survival continues to raise questions about lost chemical techniques that ancient craftsmen may have mastered through experimentation long before formal chemistry existed. The tablets from Pylos describe extensive bronze allocation systems connected to armor, spearheads, chariot equipment, and military workshops. Historians believe the palace functioned not only as a royal residence, but as a centralized industrial and military coordination center. Bronze production during this era required copper and tin sourced from distant regions. Copper likely arrived from Cyprus, while some tin may have traveled thousands of kilometers through trade routes stretching into Central Asia or Anatolia. This meant the palace depended on an enormous international supply network vulnerable to disruption. One linear date record appears to describe emergency coastal defences and preparations involving rowers and military personnel shortly before the palace's destruction. Some scholars interpret this as evidence that the rulers of Pylos feared attacks connected to the mysterious Sea Peoples, who contributed to the collapse of multiple Bronze Age civilizations around 1200 BCE. The existence of such large-scale military logistics at this early date suggests the Mycenaean world may have been far more industrialized and interconnected than previously imagined. Around 1200 BCE, Palace of Nestor was destroyed by a massive fire, but the true cause remains unknown. Some researchers blame earthquakes, while others suspect war, rebellion, or the wider collapse of Bronze Age civilizations across the Mediterranean. Strangely, many Linear B tablets were still found neatly arranged inside archive rooms, suggesting the administrative system may have continued operating until the final moments before the palace was completely consumed by flames. After the disaster, the palace was abandoned forever. The Linear B script disappeared from Greece for centuries, raising the possibility that large amounts of ancient technical knowledge vanished along with the civilization itself. What do you think really caused the fall of Palace of Nestor? Earthquake, invasion, or the collapse of an entire hidden Bronze Age network? Share your theories in the comments below. Few hours west of London, the quiet village surrounding Avebury sits inside the largest prehistoric stone circle ever built on Earth. More than 4,500 years ago, long before metal cranes, advanced mathematics, or written engineering manuals, ancient builders moved stones weighing over 100 tons, carved enormous earthworks into solid chalk, and aligned parts of the landscape with movements of the sky so precisely that some researchers still struggle to explain how it was done. Unlike Stonehenge, which appears isolated and ceremonial, Avebury feels impossibly large, less like a monument and more like an engineered landscape spread across miles of countryside. Even today, many archaeologists believe we still do not fully understand what its builders actually knew. Avebury was never truly lost, but for centuries its importance remained misunderstood. During the Middle Ages, villagers destroyed many of the stones, believing the site was connected to pagan rituals or dark supernatural forces. Some of the stones were buried deliberately, while others were broken apart for construction material. In the 17th century, antiquarian John Aubrey became one of the first scholars to document the site systematically. Later, archaeologist Alexander Keeler conducted major excavations during the 1930s, uncovering buried stones, ancient avenues, ritual pits, animal remains, and evidence that the site had once been vastly more complex than what survives today. What Keeler discovered changed archaeological history. Avebury was not a single circle. It was part of a gigantic ritual landscape linked with nearby sites, including Silbury Hill, West Kennet Long Barrow, and long ceremonial stone avenues stretching across the countryside. The scale suggested centralised planning on a level many historians once believed impossible for Neolithic Britain. The outer henge at Avebury measures roughly 331 metres in diameter, making it one of the largest megalithic enclosures ever constructed. Around it lies a massive ditch approximately 21 metres wide and up to 11 metres deep. Archaeologists estimate that ancient workers removed nearly 200,000 tons of chalk and earth, using only stone picks, antler tools, and primitive shovels. This is where the first major mystery appears. Experimental archaeology has shown that digging even a small section of the ditch using replica Neolithic tools is extraordinarily slow. Some estimates suggest the complete excavation would have required millions of labour hours, yet the ditch maintains surprising consistency in depth and angle across enormous distances. That level of uniformity implies surveying methods far more advanced than historians once expected from farming societies around 2600 BCE. The mystery becomes even greater when compared with other ancient earthworks. The Great Pyramid of Giza required highly organized labor and centralized planning, yet Egypt possessed copper tools, writing systems, and state administration. Avebury's builders had none of these advantages, and still they created one of the largest ritual constructions in prehistoric Europe. Many of the giant sarsen stones at Avebury weigh between 40 and 100 tons. Some may have been transported from the Marlborough Downs several kilometres away. Modern engineering experiments attempting to recreate stone transport using ropes, wooden rollers, sledges and manpower have produced mixed results. Moving stones across wet chalkland without modern roads is extremely difficult, even with modern understanding of friction and force distribution. Some researchers believe the builders exploited seasonal conditions, possibly transporting stones during winter when frozen ground reduced resistance. Others propose lubricated timber tracks using animal fat or water. None of these theories fully explain the efficiency needed to move dozens of stones on such a scale. Even more puzzling is the stability of the stones once erected. Many remain standing after more than 4 millennia despite exposure to storms, erosion, frost expansion, and subtle geological movement. Certain stones also appear intentionally shaped or selected according to height, texture, and orientation. This suggests the builders were not randomly placing rocks, but following an organized symbolic or astronomical system. The greatest mystery surrounding Avebury may be its relationship with the sky. Like Stonehenge, several alignments within the Avebury complex correspond roughly with solar events, particularly the summer and winter solstices. However, Avebury's layout is far more complicated than a simple solar calendar. Researchers studying the West Kennet Avenue and surrounding alignments noticed possible connections not only to the Sun, but also to long lunar cycles. One theory suggests that certain stone positions correlate with the Moon's 18.6-year major lunar standstill cycle, an extremely difficult astronomical pattern to track without generations of continuous observation. Unlike the yearly motion of the Sun, lunar standstills occur slowly and subtly. Detecting them requires careful monitoring over decades. If Avebury's builders intentionally encoded these cycles into the landscape, it would imply an astonishing level of astronomical continuity and record-keeping for a society without writing. Some archaeologists remain skeptical, arguing that enough stones exist in enough directions that certain alignments may simply be coincidence. But the concentration of celestial patterns around Avebury continues to fuel debate. The wider landscape deepens the mystery. Nearby Silbury Hill, the largest artificial prehistoric mound in Europe, may also connect visually with solar or lunar events when observed from specific points inside the Avebury complex. Some researchers believe the entire region functioned as one enormous ceremonial observatory integrated into the natural horizon itself. This idea becomes even stranger when compared with ancient astronomical systems elsewhere in the world. At Chichen Itza, the Maya engineered shadow effects linked to equinoxes. At Nabta Playa, stone circles may have tracked seasonal stars thousands of years before Stonehenge. Yet Avebury differs because its astronomical architecture is embedded across a vast open landscape rather than concentrated into a single structure. Some researchers even suggest that the moving shadows of stones, combined with ceremonial processions through the avenues, may have created a kind of living calendar where time, movement, and ritual merge together. But despite centuries of study, no single astronomical interpretation explains all of Avebury's geometry. That uncertainty is exactly what keeps the mystery alive. Modern acoustic experiments at megalithic sites have revealed unusual sound behavior around standing stones. At Avebury, low-frequency echoes and resonance effects appear in certain areas during strong wind conditions or rhythmic drumming. This matters because many prehistoric rituals likely involved chanting, percussion, and repetitive sound patterns. Researchers studying psychoacoustics suggest that low-frequency vibrations can influence human perception, producing sensations of unease, disorientation, or altered awareness. Some scientists believe ancient builders may have intentionally chosen locations with natural acoustic properties to intensify ceremonial experiences. At Avebury, the arrangement of stones may have amplified or redirected sound in ways that transformed gatherings into emotionally overwhelming events. If true, the monument may not only have been engineered for astronomy, but also for human psychology. Centuries after its original builders disappeared, Avebury still terrified local populations. During the Middle Ages, Christian authorities associated many megalithic monuments with pagan worship or demonic activity. Numerous stones at Avebury were toppled, buried, or smashed apart. One of the strangest discoveries occurred during Keeler's excavations, when archaeologists uncovered the skeleton of a medieval barber surgeon trapped beneath a fallen stone. He appears to have died while attempting to destroy it. The story spread rapidly because it felt symbolic, as though the monument itself resisted destruction. Even today, local folklore around Avebury remains filled with stories of strange lights, unexplained sensations, magnetic anomalies, and psychological unease reported by visitors walking through the stone avenues at night. Do you think Avebury was simply a ritual monument, or evidence that prehistoric civilizations understood astronomy and engineering far beyond what modern history admits? Share your thoughts in the comments below. The Mediterranean coast of southern Turkey hides Soli Pompeiopolis, an ancient city built on unstable coastal ground where earthquakes, saltwater, and erosion should have destroyed everything centuries ago. Yet massive Roman columns remain aligned with astonishing precision. Ancient harbour foundations still resist the sea, and underground engineering systems continue to survive beneath the ruins. The deeper archaeologists investigate Soli Pompeiopolis, the more the city begins to look less like a normal Roman settlement and more like a lost experiment in advanced ancient engineering. The ruins of Soli were known locally for centuries, but systematic excavations accelerated during the 20th century as archaeologists uncovered long-buried colonnaded streets, harbour structures, drainage tunnels, mosaics, and massive architectural remains hidden beneath layers of coastal sediment. Surveys revealed that much of the ancient shoreline had shifted dramatically over nearly 2,000 years, meaning large portions of the original Roman port are now partially submerged or buried inland by sediment deposits. This alone created one of the site's greatest mysteries. How did an ancient city built on unstable coastal terrain survive for so long with such structural precision? The harbour engineering of Soli Pompeiopolis remains one of the most unexplained aspects of the city. Ancient ports across the Mediterranean were constantly threatened by waves, salt crystallization, sediment buildup, and coastal collapse. Yet portions of Soli's maritime infrastructure survived far longer than many comparable ports, despite existing in an active seismic zone along the northeastern Mediterranean tectonic system. Underwater archaeological surveys have revealed massive stone blocks arranged at highly unusual angles. Rather than facing incoming waves directly, some structures appear intentionally tilted to redirect hydraulic force sideways, reducing long-term erosion pressure. Modern coastal engineers have noted that this resembles principles used in modern breakwater systems designed to dissipate wave energy instead of resisting it head-on. The strange part is that such hydrodynamic understanding should have required generations of observation and advanced empirical knowledge. Comparisons with Roman ports such as Caesarea Maritima in Israel and Pozzuoli in Italy make the mystery even deeper. In those cities, Roman engineers used volcanic ash concrete known as pozzolana. When mixed with seawater, the material chemically produced aluminum tobermorite crystals, allowing the concrete to become stronger over time. Laboratory studies published in mineralogical research journals show that some Roman marine concrete structures actually gained durability after centuries underwater. But Soli Pompeiopolis presents a problem. The region lacks the same major volcanic ash resources available near Naples, yet parts of the harbour foundations display comparable resistance to marine erosion. This has led some researchers to suspect that local engineers may have developed an alternative mineral mixture using crushed limestone, ceramic fragments, silica-rich sand, or unknown additives capable of resisting saltwater crystallization. No definitive formula has been confirmed. Even more mysterious is the harbour's apparent adaptability to shoreline migration. Geological studies suggest the coastline shifted substantially over the Roman and Byzantine periods due to sediment transported from nearby rivers and tectonic uplift. Despite this, harbour structures continued functioning for centuries. Some archaeologists believe the port may have undergone repeated recalibration and expansion using modular engineering methods similar to later Venetian maritime systems. The dimensions themselves are extraordinary. Certain submerged blocks weigh multiple tons and were positioned with surprising geometric regularity, despite being transported without cranes, steel reinforcement, or modern hydraulic equipment. Researchers comparing transport methods estimate that moving even a single large harbour stone could have required coordinated labour forces exceeding several hundred workers. Yet the final alignment accuracy rivals portions of later medieval ports built more than 1,000 years afterward. What makes Soli especially unusual is that the harbour was not merely defensive. It functioned as a large-scale commercial artery linking Cilicia to Cyprus, Egypt, Rhodes, and the wider Roman trade network. This required long-term structural reliability. A failed harbour meant economic collapse. The fact that Soli maintained maritime importance through repeated seismic activity suggests its builders possessed a far more sophisticated understanding of coastal engineering than historians once assumed. The most visually famous structure at Soli Pompeiopolis is its enormous colonnaded avenue. Dozens of granite columns still stand in partial alignment, creating one of the longest surviving Roman ceremonial streets in Anatolia. Some columns rise over 12 meters tall and weigh several tons each. What confuses engineers is not merely their size but their precision. Modern measurements show surprisingly small deviations across long distances despite centuries of earthquakes and soil movement. This is extremely difficult because coastal soil tends to compact unevenly over time. Even modern structures built on similar terrain require complex stabilization systems. Some archaeologists suspect Roman builders may have used layered sub-foundations of compacted, crushed stone beneath the avenue. Others propose that the foundations intentionally distributed load flexibility across the platform, functioning similarly to primitive seismic damping systems. Comparable techniques were later identified beneath parts of Roman roads and Byzantine foundations, but Soli appears unusually advanced for its location and age. The transportation of the granite itself creates another puzzle. Much of the stone likely originated far from the site, moving columns weighing several tons across sea routes and then erecting them with near-perfect vertical balance would have required advanced lifting systems involving pulleys, cranes, counterweights, and highly coordinated labour teams. Roman engineer Vitruvius described such technologies theoretically, but surviving evidence rarely demonstrates their execution on this scale in unstable coastal terrain. Beneath the visible ruins lies another mystery: the city's hydraulic infrastructure. Excavations uncovered underground drainage channels and water management systems built with astonishing geometric consistency. In several sections, stone channels were carved and fitted so tightly that water leakage remained minimal, even without modern mortar. Maintaining water flow across long distances requires extremely controlled gradients. A slope too steep accelerates erosion and destabilizes pressure. Too shallow, and water stagnates. Yet parts of Soli's drainage systems maintain remarkably stable inclines over extended distances, an engineering challenge difficult even with modern surveying equipment. Researchers comparing Roman hydraulic systems across the Mediterranean have noted similarities with aqueduct gradients in cities such as Nimes and Constantinople. However, Soli's systems appear compressed into a dense coastal urban environment, exposed to flooding, salt intrusion, and tectonic instability. This combination makes the precision even more remarkable. Some underground passages also suggest advanced urban planning. Drainage tunnels appear intentionally separated from freshwater transport channels, reducing contamination risks. In several sections, maintenance access points were integrated directly into the infrastructure, evidence that Roman engineers expected long-term operational management rather than short-term construction. Another unexplained feature involves the paving stones and public surfaces throughout the city. Certain road sections remain surprisingly level despite nearly 2 millennia of exposure. Erosion patterns suggest the outer stone layers may have undergone deliberate surface treatment. Microscopic analysis from comparable Roman sites has shown that repetitive polishing using quartz-rich abrasives could significantly harden exposed surfaces by reducing microfractures. Some researchers believe similar techniques may have been applied at Soli. Others suggest thermal treatment or mineral sealing methods unknown to modern archaeology. Equally strange is the drainage behavior. Some plaza surfaces appear nearly flat to the naked eye, yet still redirect rainwater efficiently. Modern urban drainage systems often rely on barely visible grading angles to prevent pooling. Soli's builders seem to have understood similar principles centuries before modern civil engineering formally documented them. Do you think ancient civilizations understood engineering far better than modern history admits? Share your thoughts and theories in the comments below. El Sheikh Hamad hides the remains of the ancient city of Dur Katlimu, a settlement that survived extreme heat, floods, earthquakes, and imperial collapse for centuries. Beneath layers of desert soil, archaeologists uncovered strange engineering systems, unusually durable mud brick structures, underground cooling chambers, and administrative records so advanced they resembled a proto-industrial logistics network. Some researchers now believe this forgotten Assyrian city possessed environmental engineering knowledge far beyond what historians once expected from the ancient Near East. The site began attracting major archaeological attention during German-led excavations in the 1970s and 1980s. Researchers identified the ruins as ancient Dur Katlimu after discovering cuneiform tablets mentioning the city directly. What initially appeared to be another mud brick settlement soon revealed something much more complex. Excavations uncovered massive storage facilities, reinforced riverbank foundations, canal systems, and thousands of administrative tablets dating between the Late Bronze Age and Neo-Assyrian periods, roughly between 1500 BCE and 600 BCE. What shocked archaeologists most was the scale of organization. Dur Katlimu was not a small provincial town. At its peak, the city controlled strategic trade moving along the Euphrates corridor connecting Mesopotamia, Anatolia, and the Levant. The number of tablets recovered suggested a bureaucratic system capable of tracking grain, labour, taxation, livestock, and military supplies with astonishing precision. Some scholars compared the complexity of the city's record-keeping to later Persian administrative systems that appeared centuries afterward. The greatest engineering mystery of El-Sheikh Hamad lies in its mud brick architecture. Across the ancient Near East, mud brick was common because stone was scarce and expensive. The problem is that traditional mud brick deteriorates rapidly under environmental stress. Heat expansion, seasonal flooding, groundwater salts, and erosion usually destroy these structures within centuries unless they're constantly repaired. Yet parts of Durkat Limu remain standing after nearly 3,000 years. This becomes even more mysterious when considering the local climate. Summer temperatures in the region regularly exceed 40 degrees Celsius, while winter moisture and occasional Euphrates flooding create severe stress cycles in earthen materials. Under such conditions, ordinary adobe construction should fracture, soften, and collapse relatively quickly. Microscopic analysis of surviving bricks revealed unusual characteristics. Some bricks appear denser than expected, with evidence of partial vitrification on outer layers, a phenomenon normally associated with low-temperature firing. Researchers found traces of clay mixed with fine gravel, organic fibers, ash particles, and mineral-rich sediments from the Euphrates floodplain. These mixtures may have functioned similarly to composite materials, distributing stress and reducing cracking. Some engineers believe the Assyrians may have unintentionally discovered a primitive stabilization process, similar to modern soil engineering. Organic fibers inside the bricks could have acted like micro-reinforcement, while ash additives may have altered moisture absorption rates. Experimental archaeology projects comparing reconstructed Assyrian bricks with standard adobe show that treated mixtures could survive significantly longer exposure to water and temperature fluctuation. The city's walls also reveal evidence of layered construction techniques. Instead of relying on single massive walls, builders often used multiple compacted layers with alternating material density. This resembles later seismic-resistant building principles used in parts of Persia and even Incan retaining systems thousands of kilometers away. The layered design may have reduced stress propagation during earthquakes or riverbank movement. Even more puzzling is the possibility that some exterior surfaces were intentionally heat-hardened after construction. Several wall fragments display mineral transformations suggesting exposure to controlled heating temperatures between approximately 400 and 700 degrees Celsius. If intentional, this would imply large-scale thermal treatment of architecture centuries before similar methods became common elsewhere in the region. No one fully understands how ancient builders developed these techniques without modern chemistry, structural engineering, or industrial kilns. Another major mystery involves the city's hydraulic engineering. Durkat Limu existed beside one of the most unpredictable rivers in the ancient world. The Euphrates could provide fertile agricultural land, but it also brought catastrophic flooding and riverbank erosion. Excavations revealed sophisticated canal networks, drainage pathways, reinforced embankments, and sediment control systems. Some riverbank foundations were constructed with alternating layers of compacted soil, gravel, and organic matter that appear specifically designed to absorb shifting pressure from floodwaters. This engineering approach resembles surprisingly modern geotechnical stabilization techniques. Similar principles are now used in flood control systems to prevent soil liquefaction and structural failure. Yet these ancient systems were built more than 2,500 years before modern hydrology emerged as a scientific discipline. Researchers also discovered evidence that water flow inside the city may have been partially regulated through elevation gradients rather than mechanical pumping. Slight changes in slope directed excess water away from residential districts while preserving underground moisture near storage areas and agricultural zones. Compared to many contemporary settlements that collapsed after repeated flooding, Durkat Limu demonstrated remarkable environmental resilience. Among the most intriguing discoveries were underground storage chambers maintaining temperatures significantly cooler than the surrounding environment. Even during intense summer heat, these subterranean facilities remained relatively stable. Archaeologists identified ventilation shafts and airflow channels positioned to maximize passive cooling through pressure differences and thermal circulation. Modern engineers comparing the structures to later Persian yakhchals and Middle Eastern wind towers found striking similarities in airflow logic. This suggests the inhabitants may have understood fundamental thermodynamic principles through empirical observation alone. Some grain storage rooms were built partially below ground with thick insulated walls and narrow openings minimizing heat transfer. Temperature simulations indicate that these chambers could preserve food supplies far longer than ordinary surface-level storage buildings in the same climate. If accurate, this would mean the people of Durkat Limu developed passive climate control architecture thousands of years before similar cooling concepts became widely documented elsewhere. The cuneiform tablets recovered from El-Sheikh Hamad reveal something equally astonishing. The city operated with extraordinary administrative complexity. Thousands of records documented food distribution, taxation, military movement, labor assignments, livestock inventories, and regional trade. The level of organization required for such management implies a highly efficient communication network connecting warehouses, officials, transport routes, and agricultural zones. Some historians estimate that maintaining this system would have required continuous coordination across hundreds of kilometers along the Euphrates trade corridor. This raises uncomfortable questions about how advanced Assyrian state infrastructure truly was. Traditional depictions often portray ancient empires as administratively primitive compared to later civilizations, but Durkat Limu suggests something closer to a centralized economic control system operating on near-industrial logistical principles. The city may not have possessed advanced machinery, but it clearly possessed advanced systems thinking. The region around the Euphrates has experienced geological activity for thousands of years, yet many parts of Durkat Limu survived for centuries. Excavations uncovered soft foundation layers made of compacted soil, gravel, and organic material beneath several major structures. Modern engineers believe these layers may have functioned like primitive shock absorbers, dispersing vibrations before they reach the upper walls. The principle is surprisingly similar to modern earthquake-resistant engineering. This suggests ancient builders may have developed construction knowledge over generations to help structures survive in an unstable geological environment. Do you think the engineers of Durkat Limu discovered construction techniques far ahead of their time? Or are we still underestimating how advanced ancient civilizations really were? Share your thoughts in the comments below. Far above the waters of Lake Nasser in southern Egypt, a lone rocky fortress still rises where entire ancient cities vanished beneath the floodwaters. Qasr Ibrim was discovered by modern archaeologists long before the construction of the Aswan High Dam, but after the dam was completed in the 1960s, the site became something even stranger, an isolated archaeological island surrounded by water and desert. Located roughly 235 kilometers south of Aswan near the old Nubian frontier, Qasr Ibrim survived while dozens of neighboring temples disappeared underwater forever. That survival turned it into one of the most important time capsules in African archaeology. Unlike most ancient cities that belong to one civilization, Qasr Ibrim contains nearly 3,000 years of continuous occupation. Egyptians, Kushites, Romans, Byzantines, and Islamic kingdoms all used the fortress without fully destroying the earlier structures. Instead, they built directly on top of older walls, chambers, and foundations. Archaeologists describe the site as a vertical historical stack where entire civilizations overlap physically. Some sections contain as many as 6 different construction phases compressed into a single wall system. This layered architecture has made excavation extremely difficult because removing one layer risks damaging another civilization beneath it. One of the greatest mysteries surrounding Casa Ibrim is its unusual structural durability. The fortress was built mainly from Nubian sandstone and mud brick, materials that normally erode rapidly under severe desert temperature fluctuations. In this region, daytime temperatures can exceed 45 degrees Celsius, while nighttime temperatures drop dramatically, causing stone expansion and contraction that slowly fractures buildings. Yet many walls at Casa Ibrim remained standing for over 1,000 years even after humidity increased following the creation of Lake Nasser. Some researchers believe ancient Nubian builders used mineral-rich Nile mud mixed with salt compounds and organic binders to create a primitive thermal-resistant mortar. Laboratory analysis detected unusually high concentrations of calcium salts and fine clay particles that may have reduced cracking. Modern experiments attempting to replicate these mixtures have produced inconsistent results, suggesting the original formula may have depended on extremely precise local materials. The mystery becomes even deeper when compared to other desert fortresses. Many Roman frontier forts in North Africa collapsed after centuries of thermal erosion, while sections of Casa Ibrim remained structurally stable despite older foundations. Some engineers compared the fortress's layered wall behavior to modern composite construction, where different material densities distribute stress more evenly across the structure. No evidence suggests the Nubians possessed advanced machinery, yet the long-term performance of the walls continues to surprise preservation experts today. Another unexplained feature is the fortress's passive cooling system. Excavations revealed underground grain storage chambers, connected by extremely narrow ventilation shafts. These shafts created controlled airflow capable of lowering interior temperatures naturally. Tests performed inside reconstructed chambers showed temperature reductions of several degrees compared to the external desert air. Some rooms also maintained remarkably stable humidity levels despite the harsh environment outside. The engineering principles resemble modern passive cooling architecture used in Middle Eastern wind towers and underground thermal storage systems. What makes this even more remarkable is the scale of food preservation. Archaeologists discovered preserved wheat, barley, dates, and seeds that survived for centuries. Organic preservation at Nile sites is normally poor because humidity and microbial activity destroy food remains quickly. At Casa Ibrim, however, the fortress itself may have created a unique microclimate. The high elevation, enclosed chambers, dry desert airflow, and thick walls combine to produce natural preservation conditions similar to controlled storage facilities. Some scholars describe the site as an accidental ancient climate-controlled archive. That archive produced one of the most important discoveries in Nubian history: thousands of surviving manuscripts. Casa Ibrim preserved documents written on parchment, papyrus, leather, wood, and textiles in languages including Egyptian, Greek, Coptic, Arabic, Old Nubian, and Meroitic-related scripts. Few sites in Africa contain such a continuous written record across so many civilizations. Some Old Nubian texts remain only partially translated today because the language itself is still incompletely understood. These documents transformed modern understanding of medieval Nubia, proving the region possessed sophisticated administration, trade systems, taxation records, and religious scholarship long after many historians assumed Nubian civilization had declined. But even the manuscripts raise strange questions. Why were they preserved so effectively here, while nearby settlements lost nearly everything organic? Some researchers suspect the fortress's internal airflow and rock insulation created a stable dry environment almost identical to modern archival preservation standards. Others believe certain storage chambers may have been intentionally engineered for long-term document protection. If true, that would suggest Nubian administrators understood preservation principles far more advanced than previously believed. The military design of Qasr Ibrim is equally mysterious. The fortress sits on steep cliffs overlooking one of the narrowest strategic corridors along the Nile. Approaching armies would have been forced through highly visible routes exposed to defenders above. Yet the internal defensive system is what confuses military historians most. Narrow corridors, restricted entry points, elevated kill zones, and overlapping wall positions resemble defensive concepts found in medieval castles built centuries later in Europe and the Middle East. Some passageways intentionally force attackers to turn sharply while climbing upward, exposing their unshielded sides to defenders. Similar strategies later appeared in Crusader fortifications such as Crac des Chevaliers, but parts of Qasr Ibrim may predate them by hundreds of years. The site also reveals evidence of advanced water management despite its isolated desert location. Maintaining a permanent population on a rocky outcrop surrounded by arid terrain should have been extremely difficult. Archaeologists uncovered cistern systems, drainage channels, and storage basins capable of collecting and preserving water efficiently. Some theories suggest the builders exploited seasonal Nile flooding combined with underground seepage and nighttime condensation. Modern researchers studying atmospheric water harvesting noted that certain stone surfaces at the fortress may have enhanced condensation during cooler desert nights, potentially increasing moisture collection naturally. Religious transformation inside Qasr Ibrim adds another layer to the mystery. Ancient Egyptian temples were later converted into Christian churches, and some of those churches were eventually transformed into Islamic structures. Yet instead of demolishing earlier architecture completely, many civilizations preserved large sections of older walls and foundations. This unusual continuity suggests later builders recognized the structural superiority of existing engineering rather than replacing it entirely. In some chambers, Christian paintings survive beside reused pharaonic stone blocks inscribed thousands of years earlier. Compared with famous archaeological sites like Petra, Masada, or Machu Picchu, Qasr Ibrim remains relatively unknown to the public. Yet, scientifically, it may be even more valuable because of its uninterrupted occupation history and exceptional preservation conditions. Petra lost most organic material. Masada preserves mainly Roman period remains. Machu Picchu existed for only a relatively short period. Qasr Ibrim, however, records nearly 3 millennia of continuous adaptation to climate, war, political collapse, and changing religions. West Kennet Long Barrow sits among the rolling chalk hills of southern England, only a few kilometres from Avebury and Silbury Hill. Discovered and excavated in detail during the 1950s and 1960s by archaeologist Stuart Piggott and his team, the site immediately shocked researchers. Beneath what looked like an ordinary grassy mound was a 100-metre-long stone tomb built around 3650 BCE, older than the Egyptian pyramids and centuries older than Stonehenge. Inside were massive sarsen stones weighing up to 2 tons, carefully engineered burial chambers, and human remains from multiple generations. But the deeper archaeologists dug, the stranger the structure became. West Kennet Long Barrow did not behave like a simple grave. It looked more like a carefully designed machine of stone, landscape, sound, and ritual, whose technology still raises questions today. The first mystery is the engineering precision of the mound itself. The structure was built using alternating layers of chalk, clay, turf, and stone in a way that distributed pressure remarkably evenly. Even after more than 5,600 years of rain, erosion and soil movement, much of the original structure remains stable. Modern geotechnical engineers studying ancient earthen monuments note that layered construction like this can reduce water penetration and internal collapse, similar to principles used in modern embankment engineering. The burial chambers were not randomly assembled either. The vertical sarsen slabs lean slightly inward, helping transfer the enormous weight of the mound away from weak points. It resembles primitive load-bearing architecture, yet the builders supposedly had no metal tools, no pulleys, and no wheeled transport. The transportation of the stones remains one of the site's greatest unsolved technological puzzles. The sarsen stones likely came from the Marlborough Downs several kilometres away. Experimental archaeologists attempting to move stones of similar size using ropes and wooden sledges discovered how brutally difficult the task would have been. On wet chalk terrain, friction becomes unpredictable, and even a 1-ton stone can become nearly uncontrollable. Yet the stones at West Kennet were positioned with impressive symmetry and alignment. Some researchers estimate that moving and placing the materials for the mound may have required coordinated labour from hundreds of people over several generations. The mystery is not simply how the stones were moved, but how Neolithic communities organised labour with such precision long before centralised states or formal engineering systems supposedly existed. Another disturbing mystery lies inside the burial chambers themselves. Excavations uncovered the remains of at least 46 individuals, including men, women and children. But the bodies were not buried normally. Many skeletons had been disarticulated, rearranged, or partially removed long after death. Some skulls showed evidence of careful defleshing using stone blades. In several cases, bones appear to have been transferred in and out of the chambers repeatedly across centuries. Archaeologists believe the monument remained active for around 1,000 years before being deliberately sealed. This suggests the site functioned less as a cemetery and more as a ritual centre where the dead remained connected to the living community. Similar practices have been identified in Neolithic tombs in Ireland and Brittany, but West Kennet shows one of the clearest examples of long-term ancestral manipulation ever found in Britain. The acoustic properties of the chambers introduce another layer of mystery. Researchers studying ancient ritual spaces discovered that the narrow stone chambers create powerful low-frequency resonance effects. A drum beat or deep human voice can produce standing waves that amplify inside the enclosed spaces. Similar acoustic phenomena have been documented in Malta's Hypogeum and certain Maya ceremonial chambers. Modern neurological studies suggest prolonged exposure to low-frequency sound around 90 to 120 Hz may alter perception, induce anxiety, or create trance-like sensations. Some archaeologists now wonder whether Neolithic builders intentionally designed enclosed chambers to manipulate psychological states during ceremonies involving the dead. If true, it would mean prehistoric communities possessed a surprisingly advanced practical understanding of sensory engineering. The mound's durability presents another scientific anomaly. Most long barrows across Britain collapsed or eroded heavily over time, yet West Kennet remains unusually intact. Geological studies indicate that the builders deliberately selected chalk and clay mixtures capable of regulating moisture movement. Chalk naturally drains water quickly, while clay slows saturation and stabilizes structural pressure. This combination acts almost like primitive waterproofing. Modern conservation engineers comparing the mound to contemporary earth structures noted that its drainage efficiency rivals some engineered embankments constructed only a few centuries ago. The question is, how Neolithic builders discovered these material properties without formal geology or engineering science? One of the most controversial theories surrounding West Kennet involves astronomy and sacred landscape design. The tomb lies within a broader ritual complex that includes Avebury Stone Circle, Silbury Hill, and ancient processional pathways. Researchers mapping the region discovered repeated alignments tied to solar movements and visibility corridors across the landscape. While not as mathematically precise as later monuments, the arrangement appears intentional. Some archaeologists believe the entire landscape functioned as a ceremonial map connecting the world of the living, the dead, and celestial cycles. Similar landscape planning appears in ancient Egypt near Giza and in parts of Mesoamerica, but West Kennet predates many of these traditions by thousands of years. The deliberate sealing of the tomb may be the strangest mystery of all. Around 2000 BCE, long after generations had used the chambers, the entrance was intentionally blocked with massive stones and tons of rubble. This was not abandonment caused by collapse. It was a deliberate closure ritual. Archaeologists found evidence that the final sealing involved careful placement of debris and selected materials, almost as if the monument itself was being buried. Why would a society spend centuries maintaining a sacred site only to deliberately shut it forever? Some researchers believe this marked a major cultural shift in Britain as older ancestor cults gave way to new Bronze Age beliefs. Others think the site may have become feared or taboo. Comparisons with other Neolithic tombs make West Kennet even more unusual. Newgrange in Ireland is famous for its winter solstice alignment, while Mashav in Orkney demonstrates extraordinary geometric planning. But West Kennet stands apart because of the combination of engineering stability, ritual reuse, acoustic manipulation, and large-scale landscape integration. It was not merely a tomb, it may have been one of the earliest examples of architecture designed to influence emotion, memory, and social identity simultaneously. Even modern technology continues revealing hidden complexities. Ground-penetrating radar surveys around the mound have identified buried features and anomalies still not fully excavated. Soil analysis detected traces of ancient organic activity beyond the visible structure, suggesting ceremonial gatherings may once have extended far outside the mound itself. Some researchers speculate that wooden structures, fires, or ritual enclosures once surrounded the site, long since erased by time. Today, West Kennet Longbarrow remains one of the clearest reminders that prehistoric societies were far more sophisticated than once believed. The monument challenges old assumptions that Neolithic communities were primitive farmers with limited technical knowledge. Instead, it reveals a civilization capable of advanced structural engineering, coordinated labor organization, environmental understanding, and possibly even psychological architecture. More than 5 millennia later, the mound still stands silently in the Wiltshire landscape, preserving secrets that archaeology has only begun to understand. The eastern Nile delta of Avaris hid the remains of a city that should not have existed at that level of technological complexity over 3,500 years ago. Massive harbour systems, advanced furnaces, engineered foundations, and international trade networks appeared in a place historians once believed was little more than swampy floodplain. Yet Avaris may have been one of the most technologically advanced cities of the Bronze Age. The ruins of Avaris were gradually identified during excavations at Tel el Dabar in the 1960s, led by Austrian archaeologist Manfred Biertak. What initially looked like scattered mud brick settlements soon revealed enormous harbour basins, palace districts, workshops, warehouses, and foreign-style architecture buried beneath meters of Nile sediment. Ground-penetrating surveys later showed that much of the city had been hidden under shifting river channels for millennia. Radiocarbon dating places the peak of Avaris between roughly 1700 and 1550 BCE during the rule of the Hyksos, a foreign dynasty that controlled northern Egypt. Ancient texts described the Hyksos as outsiders, but archaeology began showing something far more disturbing. They may also have introduced engineering systems and industrial technologies far ahead of their time. One of the greatest mysteries of Avaris is its gigantic harbour network. Excavations revealed artificial basins and canals connected directly to branches of the Nile. Some harbour areas stretched hundreds of metres wide, large enough to accommodate major cargo traffic during the Bronze Age. What shocked researchers was the precision of the hydraulic planning. Sediment analysis showed controlled water flow patterns instead of random flooding. Canal depths remained surprisingly uniform despite being dug into unstable delta soil. Maintaining navigable waterways in the Nile Delta would have required constant dredging, water management, and advanced surveying knowledge. Modern geoarchaeologists compared parts of Avaris' water system to later Phoenician and even Roman port engineering. Yet Avaris predates many of those systems by more than 1,000 years. The Nile Delta was one of the most unstable landscapes in the ancient world. River branches shifted constantly, floods reshaped the terrain every year, and soft alluvial mud could collapse engineered structures quickly. Despite this, Avaris operated as a large international port for generations. Some archaeologists believe the Hyksos may have used detailed observational hydrology, studying sediment movement, flood timing, and seasonal current changes with a sophistication never fully documented in surviving Egyptian records. The city's buildings present another unexplained engineering puzzle. Large structures in Avaris were built on waterlogged delta ground that should have been incapable of supporting heavy architecture for long periods. Yet many buildings survived for centuries. Excavations found layered sand beds, compacted mud brick platforms, reedment reinforcement, and organic stabilization materials beneath foundations. This resembles primitive soil distribution engineering, similar in principle to modern floating foundations used in unstable environments. In some districts, archaeologists discovered alternating layers of clay and sand beneath palace floors, likely designed to absorb movement caused by moisture shifts and subsidence. These methods reduce structural stress in terrain where ordinary mud brick cities should have cracked apart rapidly. Comparable stabilization systems would later appear in Mesopotamian marsh settlements and much later in parts of Venice. But Avaris demonstrates these ideas appearing extraordinarily early. Researchers still debate whether these systems evolved locally or were imported from engineering traditions outside Egypt. The most controversial discoveries at Avaris involve metallurgy. Excavations uncovered large industrial zones filled with furnaces, copper slag, molds, crucibles, tuyères, and evidence of large-scale bronze production. Some furnaces show thermal damage suggesting temperatures exceeded 1,100 degrees Celsius, high enough for sophisticated bronze alloy processing. For comparison, ordinary open Bronze Age fires rarely sustain such temperatures efficiently without advanced airflow control. The furnaces at Avaris appear to have been engineered to maximize oxygen intake through carefully angled air channels. Some researchers believe they used forced draft systems, powered either by bellows or by exploiting prevailing Nile Delta winds. The internal furnace geometry may have created natural pressure acceleration, similar to primitive blast furnace principles. This is where their mystery deepens. Several slag samples indicate remarkably consistent alloy composition. That implies controlled metallurgical processes rather than random heating. Certain bronze artifacts contain balanced tin percentages that improved hardness while preventing brittleness, knowledge requiring repeated experimentation and careful thermal control. Archaeometallurgists have compared some manufacturing precision at Avaris to later Late Bronze Age industrial centres in Anatolia and Cyprus. Yet Avaris reached this level surprisingly early. Fuel consumption also raises questions. Producing temperatures above 1,100 degrees Celsius in large numbers of furnaces should have required enormous quantities of charcoal. However, evidence for equally massive nearby deforestation remains limited. Some researchers speculate the furnace systems were unusually fuel-efficient due to airflow optimization. Even more puzzling are traces of arsenical copper production found in some areas. Arsenic bronze can produce harder tools than pure copper, but the process releases toxic fumes. Long-term production would have been extremely dangerous without some understanding of ventilation. Yet many workshop zones in Avaris were positioned to exploit dominant wind directions across the delta. Whether intentional or accidental remains unknown. Some scientists now believe Avaris functioned as one of the largest metallurgical centers in the Eastern Mediterranean during its time, a scale of industrial organization historians once thought impossible for the period. Inside elite buildings at Avaris, archaeologists discovered fragments of wall paintings unlike traditional Egyptian art. The style matched Minoan frescoes from Crete almost perfectly. Bull-leaping scenes, flowing marine imagery, layered pigments and plaster techniques all resembled artwork from Knossos over 700 kilometers away across the Mediterranean. The implications were enormous. This suggested that Avaris was connected to an international maritime trade network far larger than historians previously imagined. Some experts even proposed that Minoan artists may have physically traveled to Egypt. Pigment analysis showed imported minerals and sophisticated multi-layer painting methods requiring controlled plaster timing before drying. The techniques were highly specialized and difficult to reproduce without trained artisans. The discovery transformed Avaris from a regional Egyptian city into evidence of a deeply interconnected Bronze Age world system. Another mystery lies inside the storage complexes. Many warehouse structures appear to contain passive cooling and ventilation systems. Narrow airflow corridors, double-wall construction, elevated floors, and carefully oriented openings reduced humidity and heat build-up naturally. Experimental archaeology suggests some storage chambers may have remained several degrees cooler than outside temperatures even during hot Nile summers. For a city dependent on grain, oils, timber, copper, and imported goods, climate-controlled storage would have been essential. Moisture alone could destroy massive food reserves in the delta environment. Some engineers compare these passive systems to principles later seen in Persian wind catchers and Roman storage engineering. Again, Avaris seems to demonstrate technological solutions appearing centuries before historians expected. Avaris once served as a major center of chariot technology and military logistics in ancient Egypt. Before the Hyksos period, horses were almost unknown in Egyptian warfare, yet excavations at the site uncovered stables, chariot components, and large-scale supply infrastructure. The Hyksos are believed to have introduced composite bows and horse-drawn chariots into Egypt, permanently transforming Bronze Age warfare. Some stable areas even featured advanced drainage and ventilation systems, suggesting Avaris may have supported hundreds of horses at once, a level of logistical organization far beyond most Bronze Age cities. Do you think Avaris was simply an advanced Bronze Age city? Or evidence that ancient civilizations understood engineering far beyond what history tells us? Share your thoughts in the comments below. Northern Egypt, deep within the Nile Delta, hides the remains of Buto, a settlement older than the pyramids, buried beneath layers of mud and groundwater for over 5,000 years. What archaeologists uncovered there was not just an ancient town, but evidence of engineering, ceramic technology, and trade systems that seem impossibly advanced for prehistoric Egypt. Buto remained largely invisible for centuries because much of the site was submerged beneath Nile sediment and marshland. Modern excavations intensified during the late 20th century through German archaeological missions, led by the German Archaeological Institute. Beneath meters of alluvial mud, researchers uncovered layers dating back to around 4000, 3000 BCE during Egypt's pre-dynastic period. What shocked archaeologists was the technological complexity buried within those layers. Instead of primitive village remains, they found evidence of specialized production, long-distance trade, controlled firing technology, and surprisingly sophisticated urban planning. The greatest mystery surrounding Buto is its ceramic technology. Thousands of pottery fragments discovered at the site reveal levels of heat control that should have been extremely difficult for such an early civilization. Laboratory analysis of several ceramic samples suggests firing temperatures may have exceeded 900 degrees Celsius, with some researchers proposing temperatures approaching 1000 degrees Celsius in specific kiln conditions. For comparison, ordinary open-fire pottery from many Neolithic cultures rarely exceeded 600–700 degrees Celsius, because temperature fluctuations caused cracking and uneven mineral transformation. Yet Buto ceramics display unusually consistent coloration, dense internal structures, and reduced porosity, signs of controlled oxygen flow and sustained high heat. Even more puzzling is the appearance of early glazed or semi-glazed surfaces resembling primitive faience technology. Producing such finishes requires careful balancing of silica, alkali compounds, and temperature stability. In later Egyptian history, faience production became one of the civilization's most sophisticated chemical crafts. But at Buto, traces of these techniques appear centuries earlier than expected. Archaeologists also discovered evidence suggesting compartmentalized kiln systems rather than simple pit firing. Some ceramic fragments show nearly identical thermal exposure patterns, implying the heat inside the kiln was distributed evenly. Achieving that requires airflow management, insulation control, and fuel regulation, concepts associated with far later industrial pottery traditions. This has led researchers to compare Buto with ancient technological centers like Mehrgar and Catalhoyuk, where surprisingly advanced firing technologies also emerged long before large-scale states existed. In all three cases, archaeologists face the same question. How did prehistoric societies develop such precise thermal engineering without leaving behind transitional stages of experimentation? Some theories suggest Buto's artisans inherited forgotten knowledge from earlier Nile Delta cultures now lost beneath sediment and rising groundwater. Others believe the region may have functioned as an independent technological hub, connected to wider Near Eastern innovation networks thousands of years before formal empires emerged. Another major mystery involves the enormous trade system connected to Buto. Excavations uncovered obsidian blades whose volcanic composition points toward Ethiopia or Anatolia, copper originating from Sinai, and exotic stones unavailable anywhere in the Nile Delta. Transporting these materials across distances exceeding 1,000 kilometers during the 4th millennium BCE should have been extraordinarily difficult. Yet the volume of imported material found at Buto suggests this was not occasional exchange. It was organized commerce. This challenges older theories that pre-dynastic Egypt was composed mainly of isolated agricultural villages. Instead, Buto may have operated as a strategic trade hub linking the Mediterranean coast, the Levant, Upper Egypt, and Eastern Africa. Its location within the Nile Delta likely played a major role. At the time, the delta was not a stable landscape, but a shifting maze of marshes, lagoons, distributaries, and seasonal waterways. Navigating it required detailed environmental knowledge. Some archaeologists believe the inhabitants of Buto may have possessed advanced water navigation systems and seasonal mapping traditions long before formal cartography existed. Comparisons are often made with Mohenjo-Daro, where river-based commerce also supported surprisingly large urban networks during the Bronze Age. But Buto predates many of these systems, making its logistical sophistication even more difficult to explain. Perhaps one of the least discussed but most fascinating mysteries is how Buto survived at all. The settlement was constructed on soft Nile Delta soil, an environment highly vulnerable to subsidence, flooding, and structural collapse. Yet excavations show multiple occupation layers stacked over centuries without catastrophic destruction. Soil analysis indicates inhabitants may have intentionally stabilized foundations using compressed clay, gravel mixtures, and organic reinforcement layers. Some archaeologists compare this to primitive geotechnical engineering. The concept is astonishing because similar foundation stabilization methods are better known from much later civilizations such as Mesopotamia or Rome. In modern engineering, wetland construction requires load distribution and drainage control to prevent sinking. Somehow, Buto's builders appear to have developed basic versions of those principles over 5,000 years ago. Certain elevated sectors of the settlement also suggest deliberate landscape modification. Researchers suspect the inhabitants created artificial raised platforms to protect key structures from seasonal flooding. If confirmed, Buto would represent one of the earliest known examples of large-scale environmental engineering in Egyptian history. The artifacts discovered at Buto reveal another unresolved mystery: astonishing precision craftsmanship. Small stone beads excavated at the site contain drilled holes only a few millimeters wide, yet remarkably straight and symmetrical. Creating such perforations in hard stone with pre-dynastic technology remains controversial. Experimental archaeologists have attempted to replicate these holes using reed drills, sand abrasives, and copper tools, but reproducing the same consistency is extremely time-consuming. Several engraved ceremonial objects also display microscopic linework difficult to achieve with primitive cutting instruments. Some researchers argue this indicates the existence of specialized copper tools far earlier than traditionally believed. Comparable craftsmanship has been documented at Nakada and even in Indus Valley sites, suggesting that highly specialized artisan classes may have emerged much earlier in human civilization than once assumed. Buto's survival depended entirely on controlling water. The Nile Delta constantly shifted through flooding, erosion, and marsh expansion. Entire settlements could disappear within decades if drainage failed. Yet Buto remained continuously occupied for centuries. Archaeological surveys suggest the settlement may have included canals, drainage paths, levees, or artificially elevated zones designed to redirect floodwater. This possibility has enormous implications. Large-scale hydraulic management is usually associated with dynastic Egypt and centralized pharaonic authority, but Buto may prove that complex environmental control systems existed long before the first pharaoh unified Egypt. Some researchers even believe the delta populations developed unique ecological engineering techniques adapted specifically for marsh survival. Knowledge later absorbed into early Egyptian state infrastructure. Do you think Buto was simply an advanced settlement for its time, or evidence of a lost technological culture far older than we realize? Share your thoughts in the comments below. Tomassos sat in the center of Cyprus like a machine built for metal. Hidden between the Troodos copper belts and the trade routes of the eastern Mediterranean, the city became unimaginably wealthy more than 3,000 years ago. But the deeper archaeologists dug beneath Tomassos, the stranger it became. Underground mines with engineered airflow, smelting systems reaching temperatures above 1,200 degrees Celsius, royal tombs carved with impossible precision, and a vanished industrial civilization that may have controlled one of the ancient world's most important copper networks. The ruins of Tomassos were identified in the 19th century through inscriptions and classical references from Assyrian and Greek records. Major excavations later uncovered royal tombs, mining tunnels, furnaces, copper slag fields, hydraulic channels, and evidence of large-scale metallurgical production dating from the Cypro-Archaic and earlier Iron Age periods. Long before Rome dominated metal production, Cyprus was already one of the Mediterranean's primary copper suppliers. Ancient ships carried Cypriot copper ingots across Egypt, Anatolia, the Levant, and Greece. And some historians estimate that during parts of the Late Bronze Age, Cyprus may have produced a major percentage of the Eastern Mediterranean's traded copper. Tamassos appears to have been one of the central engines behind that system. What makes the site mysterious is not simply the amount of copper extracted, but the engineering sophistication required to sustain production at that scale. Ancient mining around Tamassos was not random digging. Archaeologists discovered organized tunnel systems following ore veins with remarkable efficiency, and in several sections, shafts appear positioned to create natural convection airflow, where hot air rose upward through vertical openings, while cooler air entered lower tunnels, creating passive ventilation deep underground. The principle is strikingly similar to modern mine airflow engineering. Without electricity, mechanical fans, or modern geological mapping, the miners somehow identified ore-bearing zones with extraordinary accuracy. Excavation waste in some shafts is surprisingly low, suggesting they were not blindly searching for copper but already understood the geology beneath them. This becomes even more astonishing when compared to many later medieval mines, which often produced far larger amounts of discarded stone relative to usable ore. Some researchers believe generations of empirical knowledge allowed Cypriot miners to read subtle mineral discolorations, fractures, groundwater chemistry, and rock temperature changes with a level of observational skill modern people underestimate. The scale itself raises even more questions. Producing bronze required enormous quantities of copper, and a single Bronze Age trade network involving weapons, tools, armor, ritual objects, and ship fittings would have consumed thousands of tons over centuries. The slag heaps around Cyprus suggest industrial activity operating continuously for generations, while some estimates place ancient Cypriot copper production in the hundreds of thousands of tons over long periods of antiquity. That kind of sustained extraction required fuel, labor organization, transportation systems, and political control that rivaled early industrial economies. And yet Tamassos eventually vanished from global importance almost completely. The metallurgical remains at Tamassos are among the site's greatest mysteries. Copper smelting requires extremely high temperatures, and to separate copper from sulfide ores efficiently, ancient furnaces likely had to exceed 1,100 to 1,200 degrees Celsius. Reaching such temperatures consistently without modern refractory materials is difficult even for experimental archaeologists today, yet chemical analysis of slag from Cyprus shows evidence of highly efficient smelting. Some furnace remains indicate controlled oxygen flow systems, probably using tuyères connected to forced air bellows, while even more surprising is the evidence that furnace interiors were coated with heat-resistant clay mixtures capable of surviving repeated thermal stress. In several areas, vitrification inside furnace walls suggests prolonged exposure to extreme temperatures. Researchers have compared some Cypriot metallurgical sophistication to Hittite and Near Eastern industrial systems, but Tamassos still stands out because of the apparent scale concentration in one region. Even stranger is the alloy consistency. Several artifacts contain carefully balanced traces of arsenic and tin. Arsenical copper can significantly increase hardness, but controlling arsenic is dangerous because toxic fumes emerge during smelting. Yet, the metal composition in some objects remains remarkably stable, implying ancient metallurgists understood repeatable material ratios rather than relying entirely on accidental experimentation. That suggests something closer to proto-material science than primitive metallurgy. The royal tombs of Tamassos remained one of the most technically impressive features ever discovered on Cyprus. Buried underground, these tomb complexes contain stairways, chambers, pillars, and carved entrances shaped directly into limestone bedrock. Several walls display unusually flat surfaces and sharply cut angles inconsistent with rough quarry extraction. The precision becomes difficult to explain when considering the available tools of the era. Bronze tools are softer than stone, and although early iron tools existed, they were still limited. Yet some chamber interiors appear almost machine-finished under certain lighting conditions. Archaeologists believe abrasives such as quartz sand may have been used for prolonged polishing and smoothing. The tomb architecture also demonstrates advanced structural understanding. Cyprus sits in an active seismic region, and the island has experienced destructive earthquakes for millennia. Nevertheless, multiple underground chambers survived partially intact for over 2,000 years. Weight distribution inside the tombs appears deliberate, with load-bearing geometry reducing collapse risk. Modern engineers have noted similar principles in Mycenaean Tholos tombs and certain Egyptian subterranean chambers, though Tamassos developed its own regional style. Some entrances were once decorated with massive stone facades and sculptural elements influenced by both Phoenician and Greek traditions, showing that Tamassos stood at the crossroads of multiple civilizations. One of the least discussed but most fascinating mysteries at Tamassos involves water management. Mining operations require constant control of groundwater and runoff, and archaeologists identified channels and drainage systems cut directly through stone near industrial zones. Some maintain remarkably stable gradients over long distances. Even small slope miscalculations can stop water flow entirely or create destructive erosion, meaning that maintaining proper hydraulic angles without laser instruments or modern surveying tools required exceptional precision. Certain channels also include sediment traps resembling primitive filtration basins, suggesting the inhabitants were not only transporting water, but actively managing impurities and flow stability. Comparisons have been made with Persian Qanat systems and Roman hydraulic engineering, yet parts of the Tamassos network may predate some later Mediterranean water technologies traditionally considered more advanced. Excavations around Tamassos uncovered jewelry, ceremonial vessels, and decorative metal objects displaying extremely fine workmanship. Microscopic examinations of engraved patterns reveal highly controlled symmetry and repeated geometric spacing. Some gold and bronze ornaments contain lines so delicate that researchers still debate the exact engraving methods used. Pigments found on several artifacts present another mystery. Blue and green mineral-based colors derived from copper compounds survive for centuries despite exposure to oxidation and moisture. Similar long-lasting pigmentation appears in Egyptian faience and certain Roman mineral paints, but the preservation quality of some Cypriot examples remains exceptional. The combination of mining expertise, alloy control, pigment chemistry, and architectural engineering makes Tamassos appear less like an isolated ancient city and more like a specialized industrial knowledge center. Do you think Tamassos truly collapsed from environmental and economic decline, or could an entire ancient industrial knowledge system have been lost to history? Share your thoughts in the comments below. About 160 kilometers north of Luxor, near the edge of the Nile Valley Desert, lies Abydos Temple Complex, one of the oldest sacred cities in Egyptian history. Archaeologists began major excavations here during the 19th century, but the site became globally controversial after researchers uncovered the massive subterranean Osiraion structure behind the Temple of Seti first. Unlike the decorated limestone temple above it, the Osiraion was built from enormous granite blocks weighing up to 70 tons each. Its engineering appeared older, heavier, and strangely disconnected from the architectural style of New Kingdom Egypt. The deeper excavations went, the stranger Abydos became. Hidden chambers, precision-cut stone surfaces, unexplained water erosion, astronomical alignments, and controversial carvings transform the site from a religious monument into one of the greatest ancient technological mysteries ever discovered. The Osirion is the single most mysterious structure in Abydos. Buried below ground level and surrounded by water channels, it looks dramatically different from the refined decorative temples of dynastic Egypt. Instead, it resembles the megalithic style seen at sites like Puma Punku in Bolivia or the platform stones of Baalbek in Lebanon. Its granite blocks are enormous, some weigh between 50 and 70 tons, and were transported from Aswan, over 150 kilometers away. Even today, moving stones of that size requires cranes, hydraulic systems, and carefully engineered transport platforms. Yet the Egyptians somehow moved, aligned, and fitted these blocks with astonishing precision over 3,000 years ago. What confuses researchers most is the construction quality. Many joints between stones are so tight that a modern razor blade cannot fit between them. Some surfaces appear machine-polished. Others contain unusually straight internal angles rarely achieved with simple copper tools. Experimental archaeology has shown that cutting granite with copper saws and quartz sand is technically possible, but reproducing Abydos-level precision requires extraordinary labor and time. Some engineers argue the efficiency implied by the Osirion simply does not match the accepted technology of the Bronze Age. Even stranger is the erosion. Several lower granite surfaces show patterns resembling prolonged water exposure. Geological comparisons have led some alternative researchers to suggest the Osirion may predate dynastic Egypt entirely, possibly originating during a wetter climatic period thousands of years earlier. Mainstream Egyptology disputes this theory, yet the erosion patterns continue fueling debate. Inside the Temple of Satyvrst, the stonework reaches a level of refinement difficult to explain using primitive tools alone. The temple walls contain thousands of deeply engraved hieroglyphs with nearly identical depth and spacing. Columns stand with near-perfect symmetry. Flat granite surfaces show deviations of only millimeters across several meters. Granite is one of the hardest stones commonly used in ancient construction. Its quartz crystals rate around 7 on the Mohs hardness scale, while copper tools rank around 3. This means the Egyptians were technically working with tools softer than the stone itself. Modern reconstructions suggest workers may have used quartz sand as an abrasive, essentially grinding the granite rather than cutting it directly. However, the precision seen at Abydos rivals certain machine-assisted masonry techniques. Circular drilling marks discovered on some Egyptian granite artifacts elsewhere in Egypt indicate penetration rates that some engineers consider unusually high for manual drilling systems. Comparisons are often made with the Inca stonework at Sacsayhuaman or the polygonal walls of Ollantaytambo. Yet Abydos differs because many surfaces here are not only tightly fitted but geometrically uniform. Some researchers speculate the Egyptians may have possessed advanced lost techniques involving vibration-assisted cutting, chemical softening of stone, or highly specialized abrasive systems never fully documented in surviving records. Among the most famous mysteries at Abydos are the so-called helicopter hieroglyphs. Located high on a temple beam, several overlapping carvings appear to resemble a helicopter, submarine, jet aircraft, and even a tank. Mainstream Egyptologists explain the phenomenon as a palimpsest, an effect created when older hieroglyphs were plastered over and later recarved by another pharaoh. Over centuries, erosion exposed both layers simultaneously, accidentally creating modern-looking shapes. Scientifically, this explanation is reasonable, yet the controversy persists because the resemblance is remarkably specific. Millions of visitors have seen the carvings, and the images spread globally as supposed evidence of lost technology or ancient knowledge. What makes the debate more interesting is not necessarily the carvings themselves, but what they represent psychologically. Abydos repeatedly confronts researchers with structures and engineering choices that already feel technologically advanced. The helicopter hieroglyphs became symbolic of a larger question: how much ancient knowledge has truly been lost? The layout of Abydos appears deeply connected to astronomy. The temple axis aligns with celestial patterns associated with Osiris, often linked symbolically to the Orion constellation. Ancient Egyptian texts repeatedly connect the soul of the pharaoh with stars in Orion's belt. During specific times of the year, sunlight travels through dark corridors and illuminates interior chambers with striking accuracy. Achieving this effect required careful calculations involving solar angles, seasonal movement, and architectural orientation. This phenomenon can also be seen at Abu Simbel, where sunlight reaches the inner sanctuary only twice per year, and at Newgrange in Ireland, where the winter solstice sun penetrates a narrow stone passage precisely at dawn. Yet Abydos contains a more labyrinth-like internal design, making its alignments especially difficult to engineer. Some archaeoastronomers argue that ancient builders possessed observational astronomical knowledge far beyond what is commonly assumed. Without telescopes or modern instruments, they tracked celestial movement accurately enough to orient massive stone complexes over long distances with minimal error. Several chambers inside Abydos produce unusual acoustic effects. Deep sounds resonate for extended periods, and low frequencies appear amplified within enclosed stone rooms. Visitors often describe a heavy vibrating sensation when speaking inside certain sections of the Osirion. Acoustic specialists studying ancient monuments have noted similar effects in Malta's Hippogeum, the Mayan pyramid at Chichen Itza, and Neolithic passage tombs across Europe. In some structures, specific frequencies can alter human perception, concentration, and emotional response. The granite used in the Osirion may also contribute to resonance behavior. Granite contains quartz crystals capable of piezoelectric effects under pressure, although no evidence proves the Egyptians intentionally used this property technologically. Still, the repeated appearance of resonance chambers in sacred ancient sites has led some researchers to question whether sound played a larger ritual or psychological role in ancient civilizations than previously believed. Modern ground-penetrating radar surveys around Abydos have revealed buried anomalies beneath the surface, including linear formations and possible voids near the Osirion. Some archaeologists believe entire sections of the ancient sacred city remain hidden beneath layers of Nile sediment. This possibility is significant because Abydos was continuously occupied and rebuilt over thousands of years. Like Troy or Jerusalem, newer civilizations repeatedly constructed temples atop older foundations. If deeper layers exist, they could potentially preserve structures from Egypt's earliest dynastic periods, or perhaps even older unknown phases of occupation. Satellite archaeology has already transformed Egyptian exploration in recent decades. Infrared imaging has revealed buried settlements, lost pyramids, and hidden road systems elsewhere across Egypt. Abydos may still conceal major discoveries waiting beneath the desert floor. One of Abydos' most historically important discoveries is the Abydos King List, a chronological sequence of pharaohs carved into the temple walls. Yet several rulers are deliberately missing, including Akhenaten, Tutankhamun, and other controversial figures connected to religious upheaval. This was not an accident. Ancient Egyptian rulers intentionally edited history. Pharaohs considered illegitimate or dangerous were removed from official records in an attempt to erase their memory entirely. The practice reveals something unsettling about ancient civilizations. Historical records were controlled narratives, not objective archives. If entire rulers could disappear from official inscriptions, researchers must ask how much additional knowledge vanished over the centuries. Do you think the mysteries of Abydos temple complex prove that ancient civilizations possessed lost knowledge far beyond what modern history accepts? Share your thoughts in the comments below. Beside the Mediterranean Sea in southern Turkey, the ruins of Soli Pompeiopolis still stand after more than 2,000 years of earthquakes, salt corrosion, coastal storms, and shifting ground. Massive granite columns remain upright. Harbour foundations still survive beneath layers of sediment. Even stranger, some of the ancient mortar exposed to seawater appears stronger today than when it was first poured. Archaeologists expected another ruined Roman port. Instead, they found traces of engineering knowledge that still cannot be fully replicated. The site was first documented by European travellers during the 19th century, but systematic excavations accelerated in the 20th century after large portions of the ancient city were found beneath farmland and coastal sediment. Archaeologists uncovered a monumental colonnaded avenue stretching over 200 metres long, harbour structures buried beneath marine deposits, drainage systems, bath complexes, mosaics, and foundations of sea-facing defensive walls. Geological surveys later revealed something unexpected. Much of ancient Soli had been altered by shoreline movement, sediment accumulation, and possible seismic events. Parts of the original harbour now lie inland, while other sections may still remain underwater. Ground-penetrating radar and sonar scans continue to reveal hidden structures beneath both the soil and the sea. What emerged was not merely a Roman port city, but a technologically sophisticated maritime centre that may have possessed engineering solutions centuries ahead of its time. One of the greatest mysteries surrounding Soli is its harbour system. Ancient Mediterranean ports usually suffered from rapid sediment buildup. Harbours in Egypt, Phoenicia, and parts of the Levant often required constant dredging because coastal currents carried enormous quantities of sand and silt into docking zones. Yet Soli remained operational for centuries. Marine geology studies suggest the harbour may have been designed to manipulate coastal currents rather than resist them directly. Some surviving breakwater stones appear angled in ways that redirect water flow, potentially creating rotational circulation patterns capable of reducing sediment accumulation naturally. Modern coastal engineers have compared this concept to self-flushing harbours, systems designed to use hydrodynamic pressure to clear debris automatically. The strange part is that the mathematics behind these flow control systems were not formally understood until much later in history. Researchers studying Mediterranean sediment transport noted that even small angular changes in barrier placement can dramatically alter erosion patterns. At Soli, several submerged stone alignments appear deliberately positioned according to prevailing current directions rather than simple defensive geometry. If intentional, this would mean Soli's builders understood long-term marine behaviour with astonishing precision. Some archaeologists remain cautious, arguing the patterns may be coincidental, but others point out that similar hydraulic awareness appears at Caesarea Maritima, Alexandria, and certain Phoenician ports, though rarely with the same apparent resistance to sediment burial seen at Soli. The deeper excavations go, the more the harbour begins to resemble an ancient maritime laboratory. Among all the mysteries at Soli, none may be more scientifically important than its mortar. Most modern concrete deteriorates rapidly in marine environments. Saltwater penetrates microscopic cracks, corrodes reinforcement materials, weakens internal bonds, and eventually fractures the structure from within. Many modern harbour systems require major repairs within 50 to 100 years, yet portions of Soli's coastal foundations have survived for over 2 millennia. Material analysis performed on Roman marine concrete from Mediterranean sites has shown that ancient builders often mixed lime with volcanic ash containing pozzolanic minerals. When seawater entered the concrete, chemical reactions continued inside the material for centuries, gradually forming rare crystalline structures such as aluminous tobermorite and philipsite. These minerals are extremely resistant to cracking. In modern engineering, this process is astonishing because seawater normally destroys concrete. Ancient Roman marine mortar appears to do the opposite. The salt water actually strengthens it over time. Some samples associated with coastal ruins near Soli show unusually dense crystalline growth compared to standard Roman concrete. Researchers suspect local mineral compositions from the Cilician coast may have enhanced long-term durability even further. Scientists from modern materials laboratories have attempted to recreate Roman marine concrete using volcanic ash from Italy and experimental seawater curing processes. While some results show impressive durability, no modern recreation has perfectly matched the lifespan of the ancient material. This has created an uncomfortable question for modern engineering. How did ancient builders accidentally produce a marine concrete formula capable of surviving longer than many modern coastal structures? Even more mysterious is the possibility that the process was not accidental at all. Certain ancient construction texts imply Roman engineers carefully selected different volcanic materials, depending on whether structures would face fresh water, humidity, or direct seawater exposure. If true, that suggests a level of empirical chemical knowledge far more advanced than historians once believed. At Soli, the surviving harbour foundations may represent one of the clearest examples of this forgotten material science. And despite satellites, laboratories, and modern computational modelling, humanity still cannot fully reproduce it. The famous Avenue of Soli once held nearly 200 granite columns, many standing 8 to 9 metres tall and weighing several tons each. Granite sources capable of producing stones of this scale do not exist near the site itself, meaning the material had to be transported over enormous distances. Ancient engineers somehow quarried, shaped, transported, unloaded, and erected these columns with remarkable consistency. The logistical challenge alone is staggering. Experimental archaeology suggests moving a single multi-ton granite column using traditional sled systems could require dozens of workers, lubrication techniques, wooden rollers, and carefully synchronized force distribution. Yet Soli imported enough stone to line an entire monumental avenue. Some researchers believe ancient maritime cranes and pulley systems may have been far more advanced than traditionally assumed. Others point to unusual spiral scoring marks found on certain stone surfaces that may indicate rotational lifting or controlled rolling mechanisms. Even more intriguing is the stability of the surviving columns. Southern Anatolia is highly seismic, yet many foundations endured repeated earthquakes. Beneath several column bases, archaeologists identified compacted gravel and layered mortar systems that may have acted as primitive shock absorbers. Comparable seismic engineering has been observed in parts of Peru, Roman Italy, and even certain Hellenistic structures, but Soli remains one of the least discussed examples. The possibility that ancient builders intentionally designed flexible anti-seismic foundations centuries before modern earthquake engineering remains controversial, but increasingly difficult to dismiss. Modern sonar scans suggest parts of ancient Soli Pompeiopolis may still lie beneath the Mediterranean. Researchers have detected geometric formations offshore that resemble harbour walls, foundations, and buried structures hidden under sediment. Some underwater alignments do not match today's coastline, suggesting ancient seismic events or tsunamis may have reshaped the region centuries ago. But some archaeologists believe the visible ruins are only a small part of the original port city. Each new scan reveals more submerged walls, platforms, and linear structures that should not still survive after thousands of years underwater. And the deeper researchers investigate, the bigger the mystery becomes. How much ancient engineering knowledge disappeared beneath the sea with Soli? What do you think is still hidden beneath the waters of Soli? Could an entire ancient harbour city still be waiting to be discovered? Share your thoughts in the comments below. Northeast of modern Zagazig in Egypt's Nile Delta, Bubastis hides beneath layers of mud and broken stone. Ancient writers claimed hundreds of thousands gathered here to worship Bastet, the feline goddess. But beneath the collapsed temples and cat cemeteries lies something stranger. Evidence of engineering systems, industrial-scale animal mummification, and construction methods that still puzzle archaeologists today. Unlike Giza, Bubastis was not preserved by dry desert sands. The city sat in the wet Nile Delta, where water, mud, salt and agriculture slowly buried and destroyed ancient structures over centuries. Modern excavations at Tel Basta began seriously during the 19th century through the work of Edouard Naville and later Egyptian teams. What they uncovered shocked historians. Massive granite columns, underground drainage systems, workshops, industrial-scale embalming areas, and enormous cemeteries filled with animal remains. The most surprising detail was location. Bubastis stood on unstable floodplain soil, not solid desert plateau, yet many structures survived for over 2,500 years despite constant groundwater pressure and Nile flooding cycles. One of the greatest mysteries surrounding Bubastis is the presence of enormous granite and basalt blocks in the middle of the Nile Delta. Granite is not naturally found there. Most of the stone likely came from Aswan, over 800 kilometers south. Some surviving column fragments weigh several tons. Transporting stone of that scale across the Nile was already difficult. Moving it through marshlands and unstable delta terrain without modern cranes or steel machinery seems even more improbable. Archaeologists estimate that moving a single 20-ton granite block using traditional wooden sledges would require dozens of workers and carefully controlled lubrication systems using water or mud. Reliefs from other Egyptian sites show workers pouring liquid beneath sledges to reduce friction, a principle similar to modern tribology. But Bubastis raises a larger question. How was such transportation organized repeatedly on an industrial scale? Even more mysterious is the polish quality of certain granite surfaces. Some columns from Bubastis show reflective finishes comparable to royal temples at Karnak. Granite ranks around 6 to 7 on the Mohs hardness scale, far harder than copper tools commonly used in ancient Egypt. Experimental archaeology suggests workers may have relied on quartz sand abrasion, dolerite pounding stones, and extremely long polishing processes. Yet the precision achieved still surprises many engineers today. Comparisons are often made to the stonework of Peru's Sacsayhuaman or the basalt blocks of Baalbek in Lebanon. In all three cases, ancient builders somehow manipulated massive stone with precision that seems disproportionate to the tools officially available to them. Bubastis may contain one of the most underrated engineering achievements in ancient Egypt: foundation stabilization technology. The city was constructed on soft alluvial soil saturated with water for much of the year. In modern civil engineering, heavy stone structures on such terrain normally require deep piling systems or reinforced foundations to prevent uneven settlement. Yet many temple sections at Bubastis remained standing for centuries. Excavations revealed layered foundation beds made from compacted sand, mud brick, rubble, and crushed stone. Instead of relying on one solid platform, the builders created multiple compression layers capable of distributing structural weight across unstable ground. The technique resembles primitive load diffusion engineering. Some researchers compare this system to seismic foundation concepts later seen in parts of the Inca world, or flood-adapted urban construction in Mohenjo-Daro from the Indus Valley civilization. The comparison becomes even more remarkable considering Bubastis predates many advanced Roman engineering systems by centuries. Satellite imaging and soil analysis also suggest the city's planners understood seasonal flood behavior extremely well. Key temple structures were positioned slightly above surrounding terrain, minimizing long-term water damage. That level of environmental adaptation implies a deep practical understanding of hydrology and soil mechanics. Beneath Bubastis, archaeologists uncovered channels, reservoirs, and drainage pathways designed with surprisingly accurate gradients. Water appears to have flowed through parts of the city using gravity alone. Maintaining drainage in the Nile Delta is extraordinarily difficult. Even today, engineers must constantly manage groundwater levels to prevent flooding and soil collapse. Yet Bubastis functioned for centuries in one of the wettest regions of ancient Egypt. Several underground sections were lined with waterproof materials whose exact composition remains debated. Chemical analyses suggest mixtures containing silicates, lime compounds, and organic additives that reduced cracking over time. Some scholars compare the durability of these materials to early forms of hydraulic concrete. This has led to controversial discussions about whether Egyptian builders possessed more advanced chemical knowledge than traditionally assumed. Similar debates surround Roman marine concrete, which remained durable for over 2,000 years because of volcanic ash reactions forming rare mineral crystals. Bubastis may represent an earlier and less understood experimentation with long-lasting waterproof construction materials. The most disturbing and technologically mysterious aspect of Bubastis is the scale of its cat mummification industry. Excavators discovered enormous cat cemeteries containing hundreds of thousands of mummified cats. Some estimates across Bastet cult centers in Egypt reach into the millions. Bubastis appears to have been one of the largest production centers. This was not a random burial. The process required astonishing logistical coordination. Each mummy demanded linen wrapping, natron salts for dehydration, resin compounds, oils, and careful preservation techniques. Experimental studies show complete mummification could take around 40 days depending on body size and environmental conditions. Maintaining such operations continuously would require organized breeding systems, storage facilities, chemical preparation workshops, and trained embalmers. CT scans performed on some animal mummies revealed additional mysteries. Many cats died at very young ages, suggesting deliberate breeding and ritual sacrifice programs. Others contained broken necks consistent with controlled killing methods. Some bundles contained partial remains, or even substitute materials instead of full skeletons, implying mass production pressures within the cult economy. The wrapping quality itself is extraordinary. Certain cat mummies display geometric linen patterns with near-perfect symmetry. Textile specialists note that achieving such consistency required advanced weaving methods and highly standardized embalming procedures. Researchers have compared the scale of the operation to proto-industrial production systems. Ancient workers were effectively managing supply chains involving animal breeding, chemical processing, textile production, religious distribution, and burial logistics on a massive scale. The resin chemistry remains another major puzzle. Some analyses detected imported compounds likely originating from Levantine forests or regions farther south. This suggests Bubastis was connected to long-distance trade networks capable of moving specialized embalming ingredients across hundreds or even thousands of kilometers. In many ways, the cat necropolis of Bubastis looks less like a simple religious cemetery and more like one of the ancient world's earliest large-scale ritual industries. Ancient Greek historian Herodotus described Bubastis as one of the most beautiful temple cities in Egypt. Modern surveys reveal that several temple axes may align with solar events and possibly the heliacal rising of Sirius, the star deeply associated with Egyptian calendrical cycles. The The precision is remarkable considering the likely tools available. Some alignments deviate only a few degrees from key astronomical positions. Egyptian priests may have combined shadow measurements, star observations, and horizon tracking to orient structures with surprising accuracy. This mirrors patterns seen at Chaco Canyon in North America, Nabta Playa in southern Egypt, and the Maya observatories of Central America. Across multiple ancient civilizations, astronomy appears repeatedly linked to architecture, ritual timing, and urban planning. Excavations also uncovered evidence of advanced copper alloy production. Some metal tools contained arsenic and tin ratios that improved hardness without making the metal excessively brittle. Arsenical bronze is particularly dangerous to produce because heating arsenic minerals releases toxic fumes. Sustained production would have required practical metallurgical knowledge developed through generations of experimentation. Microscopic analysis of surviving tools suggests repeated heating and hammering cycles were used to strengthen metal edges. This resembles later metallurgical techniques associated with work hardening. The existence of specialized workshops at Bubastis hints at organized craft industries operating under centralized control. Rather than isolated artisans, the city may have supported coordinated manufacturing sectors tied directly to temple economies. Do you think Bubastis was simply an advanced ancient city, or evidence that parts of Egyptian technology were far more sophisticated than history admits? Share your thoughts in the comments below. Northern Jordan, near the modern border with Syria and overlooking the Sea of Galilee, archaeologists uncovered an enormous underground necropolis beneath the ruins of ancient Gadara, today known as Saiz. Initial excavations in the late 19th and early 20th centuries revealed hundreds of tomb chambers hidden beneath layers of collapsed basalt rock. What appeared at first to be a typical Greco-Roman cemetery soon became something far stranger. The deeper researchers explored, the more they realized this necropolis was carved not into soft limestone or sandstone, but into dense volcanic basalt, one of the hardest construction stones used in the ancient world. That single fact changed everything. Basalt is dramatically more difficult to cut than the sandstone of Petra or the limestone used around Rome. Modern geological measurements place basalt around 6 on the Mohs hardness scale, while many limestones range closer to 3 or 4. Even with modern steel tools, quarrying basalt remains slow and energy-intensive. Yet beneath Kayas lies a maze of corridors, burial chambers, ventilation shafts, stairways, and vaulted ceilings, extending through massive black volcanic bedrock with surprising precision. For archaeologists, the necropolis created an uncomfortable question. How did an ancient civilization, working nearly 2,000 years ago, carve such an enormous underground complex into volcanic stone with tools that should have been far less effective? The mystery begins with the walls themselves. Many corridors inside the necropolis contain long parallel cutting marks unusually straight for hand chiseling. In several chambers, the surfaces appear almost machine-smoothed, with sharp geometric corners and consistent ceiling curvature. Roman and Hellenistic builders were undoubtedly skilled engineers, but the scale of labor implied here is staggering. Some estimates suggest that removing even a single cubic meter of basalt using traditional iron chisels could require dozens of man-hours. Yet the Kay's network contains thousands of cubic meters of excavated stone. The engineering challenge becomes even more impressive when compared to other ancient underground sites. Roman catacombs near Rome were usually dug into soft volcanic tuff, a lightweight rock easy to carve. Cappadocia's underground cities in Turkey were excavated into soft ignimbrite. Petra's monuments were carved into relatively workable sandstone. Kay's, by contrast, demanded excavation through dense basalt capable of dulling iron tools rapidly. Despite this, Many chambers remain geometrically symmetrical, suggesting highly organized planning rather than gradual random digging. Even more mysterious is the necropolis ventilation system. Some burial chambers descend several levels underground, yet air circulation inside remains surprisingly stable. Archaeologists identified narrow shafts and side tunnels too small for human movement, but perfectly positioned to redirect airflow. Researchers suspect these acted as primitive pressure-balancing channels, creating natural ventilation through temperature differences between the surface and underground chambers. Similar passive airflow principles appear in Persian wind catchers and Cappadocian underground cities, but Umkais applied them inside volcanic rock with remarkable efficiency. The physics behind this is significant. Basalt absorbs and retains heat far longer than softer sedimentary stone. During the daytime, surface basalt heats intensely under the Jordanian sun, then slowly releases heat after sunset. By strategically placing narrow shafts between warm and cool zones, ancient builders may have created convection-driven airflow systems without mechanical assistance. Some modern engineers studying passive cooling architecture note that such thermal regulation principles resemble techniques used in contemporary sustainable building design. But airflow was only part of the puzzle. Humidity control inside the necropolis remains equally difficult to explain. Despite centuries underground, several burial chambers remained unexpectedly dry compared to neighboring archaeological sites in the Levant. Researchers found traces of mineral coatings and mortar mixtures containing volcanic ash and fine aggregates similar to Roman pozzolanic concrete. Roman marine concrete famously hardened over time through chemical reactions involving volcanic material, allowing harbours to survive for millennia. At Umkais, microscopic analysis suggests certain wall coatings may have functioned similarly, helping resist cracking and moisture penetration inside basalt chambers. What makes this unusual is geography. Jordan was not the centre of Roman volcanic concrete production. Most advanced pozzolanic formulas originated near Italian volcanic regions around Naples, yet Umkais appears to contain local adaptations of comparable technology. Some researchers believe engineers transported technical knowledge across the Eastern Roman Empire, while others argue the formulas were independently modified using regional volcanic materials. Either explanation implies a far more advanced exchange of engineering knowledge than traditionally assumed. Then there are the tomb alignments. Several chambers inside the necropolis appear oriented toward precise solar positions during seasonal transitions. During particular days of the year, sunlight entering narrow openings can briefly illuminate central sarcophagi deep underground. This phenomenon resembles solar alignments found at sites like Newgrange in Ireland or Abu Simbel in Egypt, where architecture interacted deliberately with celestial cycles. But accomplishing such precision underground inside basalt corridors required extraordinary geometric planning. Researchers still debate whether these alignments were symbolic, astronomical, or ritualistic. Ancient Gadara was a multicultural city influenced by Greek, Roman, Nabatean, and Semitic traditions. The necropolis may therefore represent a fusion of funerary beliefs combining astronomy, cosmology, and engineering. In many ancient societies, sunlight symbolized rebirth or passage into the afterlife. The fact that light penetrated certain Umkais chambers only briefly each year may not have been accidental. Ground-penetrating radar surveys added another layer to the mystery. Subsurface scans revealed multiple hidden voids beneath already excavated sections of the necropolis. Some cavities remain inaccessible due to collapse risks and unstable geology. Preliminary data suggests the underground complex could be significantly larger than currently mapped. If confirmed, Umkais may rival portions of Rome's catacombs in scale, while being carved through vastly harder stone. And that raises an even bigger question. Why construct such an enormous necropolis in basalt at all? From an engineering perspective, easier alternatives existed nearby. Softer stone formations would have reduced labour dramatically, yet the builders deliberately chose volcanic bedrock. Some archaeologists argue basalt symbolised permanence and endurance. Others suggest the elevated volcanic plateau offered structural stability and natural defence against erosion. But another possibility exists. Ancient engineers may have understood basalt's long-term resistance to humidity, collapse, and seismic damage better than modern historians realise. That theory becomes especially important in a region shaped by earthquakes. Kayes lies near the Jordan Rift Valley, part of the tectonic boundary associated with the Dead Sea Transform Fault System. Historical records document major earthquakes across the region for centuries. Many ancient cities nearby suffered catastrophic destruction, yet portions of the Kayes necropolis survived remarkably intact underground. Several chambers feature subtly curved vaulted ceilings, distributing pressure away from structural weak points, similar to anti-seismic load distribution used in later Roman engineering. In some tunnels, archaeologists observed intentionally narrow passage transitions between larger chambers. Modern structural engineers recognize that such bottleneck geometry can reduce stress propagation during seismic movement. Whether ancient builders understood earthquake mechanics scientifically or through accumulated experience remains unknown, but the survival of these underground spaces suggests they possessed far greater geological awareness than often assumed. Heraclea at Latmus sits beside Lake Bafar in western Turkey, surrounded by colossal granite mountains that look almost artificial. Here, massive defensive walls climb impossible slopes, prehistoric rock paintings cover remote cliffs, and ancient water systems still survive after more than 2,000 years. Archaeologists still cannot fully explain how a city built onto rain this hostile managed to engineer stone fortifications, waterproof reservoirs, and complex infrastructure that rivaled far larger civilizations. The ruins of Heraclea at Latmus became widely studied during 19th century European archaeological surveys across Anatolia. Early explorers were shocked by the scale of the fortifications hidden among the granite formations of the Latmus Mountains. Later excavations revealed something even stranger. The region was not occupied by only one civilization. Around the city, researchers discovered prehistoric rock paintings dating back nearly 8,000 years, centuries before classical Greek settlement ever appeared there. Scientific analysis later showed that Heraclea originally stood close to the Aegean coastline. Over thousands of years, sediment carried by the Buyuk-Menderes River slowly pushed the sea away, transforming the harbour into marshland and eventually into the modern Lake Bafar region. This meant the city survived dramatic environmental changes that would have destroyed many ancient settlements dependent on maritime trade. The first major mystery of Heraclea is its location itself. Most ancient Greek cities were built on relatively manageable terrain, where transportation and construction were practical. Heraclea ignored that logic completely. The city was constructed directly among enormous granite boulders, many rising over 20 meters high, with steep inclines and unstable surfaces that remain difficult even for modern climbers. Despite this, the inhabitants built defensive walls stretching roughly 6.5 kilometers. Some sections still stand over 10 meters tall. The stones used in the fortifications weigh several tons each, yet many were fitted together with extraordinary precision. Archaeologists have compared portions of the masonry to the polygonal stonework found at Mycenae and even certain defensive sectors of Pergamon. However, Heraclea's terrain is significantly harsher. The engineering challenge becomes even more difficult when considering transportation. Ancient builders would have needed to move heavy stone blocks uphill through fractured granite landscapes without advanced machinery. Researchers estimate that some blocks required coordinated labour forces of dozens of workers. Yet there is little evidence of the wide transport roads usually associated with large-scale ancient construction projects. Some historians believe the builders used the mountain itself as part of the architecture rather than attempting to reshape it. Walls were often connected directly into natural rock formations, creating a hybrid defensive system between natural geology and human engineering. This technique resembles certain Andean fortifications in Peru more than traditional Greek urban planning. Heraclea's defensive system was not simply large, it was strategically sophisticated in ways that continue to surprise military historians. Watchtowers were positioned to maximize visibility across narrow mountain corridors and lake approaches. Instead of relying on flat defensive perimeters, the builders created overlapping observation zones using elevation differences and natural rock barriers. Modern analysts sometimes describe this as an early form of terrain-optimized warfare engineering. Certain tower positions allowed defenders to monitor enormous areas while remaining extremely difficult to attack directly. Similar principles would later appear in Byzantine mountain fortresses nearly 1,000 years afterward. Even more unusual is the way some walls curve around granite formations instead of cutting through them. This reduced construction effort while also increasing defensive unpredictability. Invading forces could not easily anticipate blind corners or elevated ambush positions. The landscape itself became part of the weapon system. The greatest technological mystery of Heraclea may not be its walls, but its survival systems. Water management in mountainous terrain is extraordinarily difficult. Seasonal droughts, shifting shoreline conditions, and unstable runoff patterns would have constantly threatened the city's population. Yet archaeological surveys uncovered an extensive network of cisterns, channels, carved reservoirs, and stone-cut storage systems integrated directly into the mountain. Some reservoirs were carved into granite itself and coated with waterproof materials that still remain partially functional today. This is one of the most debated aspects of the site. Granite is notoriously difficult to seal because microscopic fractures allow slow water leakage over time. Yet certain Heraclea reservoirs retained structural integrity for more than 2 millennia despite earthquakes, climate changes, and erosion. Researchers studying the remaining plaster layers found evidence of mineral-based waterproof compounds, possibly containing lime mixtures, volcanic additives, and finely processed aggregates similar to Roman hydraulic concrete. The comparison with Roman engineering is important because many Roman waterproof systems relied on pozzolanic ash mixtures, capable of chemically reacting with water to strengthen over time. However, Heraclea's systems appear adapted specifically for mountainous granite environments rather than coastal harbour construction. Some channels were designed to redirect runoff during heavy seasonal rains, preventing sudden flooding from destroying the city's infrastructure. Others appear connected to long-term storage systems that could preserve water through dry periods. This level of environmental adaptation suggests advanced hydrological understanding, far beyond what most people associate with smaller Hellenistic settlements. Researchers have also noted similarities between Heraclea's water systems and ancient Persian water management traditions such as qanat engineering, where water pressure, slope control, and underground distribution were carefully calculated. Whether these similarities emerged independently or through cultural exchange remains uncertain. Perhaps the strangest detail is durability. Certain waterproof coatings survived far longer than many medieval mortars exposed to similar conditions. Some experts believe the builders may have discovered local mineral combinations uniquely suited for granite adhesion. If true, it would mean Heraclea possessed regional engineering knowledge that was highly specialized and later lost. Long before Heraclea became a Greek city, the Latmus Mountains were already sacred. Hundreds of prehistoric rock paintings discovered across the region date back roughly 8,000 years to the Neolithic era. Unlike many prehistoric sites dominated by hunting imagery, Latmus paintings frequently depict groups of humans standing together, ritual gatherings, geometric symbols, and unusual paired figures. This has led some archaeologists to propose that the mountains served ceremonial or cosmological purposes rather than purely survival-based activities. Several rock formations in the region naturally align with sunrise positions during specific times of the year. Narrow gaps between granite towers create framed solar viewing points, resembling primitive observation corridors. Although no definitive astronomical observatory has been confirmed, researchers continue investigating whether the area functioned as an early ritual landscape connected to seasonal cycles. Comparisons are often made to sites such as Chaco Culture National Historical Park and Nabta Playa, where prehistoric communities appear to have integrated landscape geometry with celestial observation. The Temple of Athena at Heraclea contains another unresolved puzzle. Some granite foundation stones display cutting marks with surprisingly straight channels and smooth surfaces. Granite ranks among the hardest natural building stones, and shaping it requires enormous effort even with iron tools. Yet, several blocks appear cut with a consistency difficult to explain through primitive hammering methods alone. Similar debates exist at Baalbek, Ollantaytambo, and parts of ancient Egyptian stonework. Mainstream Astuta archaeology attributes such precision to long-term labor, abrasion techniques, and advanced craftsmanship rather than lost high technology. Still, Heraclea adds another example to the growing list of ancient sites where stone engineering appears more sophisticated than expected for the era. Another lesser-known mystery involves sound. Certain granite corridors and cavities within the Latmus Mountains produce unusually long echoes and resonance effects during strong winds or loud noises. Some researchers suspect these acoustic zones may have influenced ritual activity in the region for thousands of years. Natural amphitheatre-like formations can amplify voices across surprising distances without artificial construction. In a landscape already associated with ritual paintings and sacred symbolism, these acoustic effects may not have gone unnoticed by ancient inhabitants. Modern acoustic mapping in rocky archaeological environments has shown that many ancient ceremonial sites were intentionally selected for their sound properties. Whether Heraclea's surrounding mountains were chosen partly for this reason remains an open question. Perched on limestone cliffs nearly 70 meters above the Mediterranean coast of Cyprus, Kourian archaeological site was destroyed in seconds by one of the most violent earthquakes of the ancient world. Yet beneath the collapsed columns and shattered villas, archaeologists discovered something unsettling, evidence that this city may have possessed engineering knowledge centuries ahead of its time. Modern excavations at Kourian accelerated during the 1930s under the direction of the University Museum of the University of Pennsylvania. What researchers uncovered was extraordinary. Entire districts frozen in the exact moment of destruction, caused by the massive earthquake of 365 AD, an event now estimated between magnitude 8.0 and 8.5. Bodies remained trapped beneath collapsed roofs. Stone columns had fallen in identical directions. Mosaics survived while surrounding walls disintegrated, and even today, Kourian remains one of the clearest archaeological earthquake snapshots ever discovered in the Roman world. The first mystery of Kourian begins with its location itself. The city was constructed directly above unstable coastal cliffs within one of the most seismically dangerous regions in the eastern Mediterranean. Cyprus lies near the boundary between the African and Eurasian tectonic plates, where stress accumulation has triggered destructive earthquakes for thousands of years. Modern geological surveys show the limestone beneath Kourion contains natural fractures capable of amplifying seismic waves. Under ordinary engineering logic, this should have made the site unsuitable for large stone architecture. Yet for nearly 700 years, Kourion supported massive Roman bath complexes, multi-story villas, aqueduct systems, granite columns weighing several tons, and a theatre capable of holding around 3,500 spectators. What confuses researchers is how the city remained structurally stable for centuries despite constant tectonic instability. Some engineers now believe the builders of Kourion understood practical earthquake behavior through long-term observation rather than mathematics. Similar patterns appear in ancient earthquake-resistant structures elsewhere in the Mediterranean, including Parthenon, Temple of Apollo at Delphi, and Pont du Gard. But Kourion may represent one of the most advanced examples, because the entire city functioned on unstable coastal geology. One of the strangest discoveries at Kourion involves the way its buildings absorbed seismic force. Archaeologists found that many stone blocks were not rigidly cemented together. Instead, certain columns and foundation layers used flexible contact zones, allowing slight movement during tremors. In modern engineering, this resembles primitive seismic isolation systems. Some foundations contained alternating layers of crushed stone beneath heavier masonry, and these layers may have acted as shock absorbers, dispersing energy before it reached upper structures. The same principle appears in modern anti-earthquake architecture used in Japan and California. The theatre of Kourion is especially puzzling because despite repeated earthquakes over nearly 2 millennia, much of its curved seating structure survived remarkably well compared to nearby rectangular buildings. Researchers studying ancient structural mechanics noticed several unusual features. Curved geometry distributed stress more evenly, stone seating rows acted as interlocking stabilizers, and open-air construction reduced roof collapse pressure. Even more mysterious is the precision of the load distribution. Modern simulations suggest some sections of Kourion's architecture approach stability ratios comparable to later Byzantine seismic designs developed centuries afterward. No surviving Roman texts fully explain how such engineering knowledge was standardized. Kourion ancient theatre is not only structurally strange, it also possesses unusually advanced acoustic behavior. Today, visitors standing at the center of the stage can still be heard clearly from the upper seating rows, despite intense sea winds from the Mediterranean coast. Acoustic tests conducted at similar Greco-Roman theatres show speech intelligibility often remains above 90% across large seating areas without amplification. At Kourion, the geometry appears almost mathematically optimized. The semicircular arrangement minimizes echo distortion. Limestone surfaces reflect mid-frequency human speech efficiently, and the slope angle enhances sound projection naturally. What makes this mysterious is that the theatre predates formal acoustic science by more than 1,000 years. Ancient architects seemingly achieved sophisticated sound engineering entirely through empirical experimentation. Comparable acoustic anomalies exist at Epidaurus Ancient Theatre and Aspendos Theatre. Yet Kourion's exposure to ocean winds should theoretically reduce clarity significantly. Instead, the site still produces highly intelligible sound conditions even today. The greatest mystery of Kourion lies inside the house of Eustolios. More than 1,500 years after the earthquake, many mosaics still preserve astonishing color intensity despite exposure to moisture, salt air, temperature fluctuations, and structural collapse. For conservators, this should not happen. Scientific analysis of the mosaics revealed several extraordinary characteristics. Mineral pigments contained unusually stable iron oxides and copper-based compounds. Lime mortar layers displayed extremely low salt penetration, and tesserae placement reduced internal cracking during seismic vibration. Some sections maintain visible detail after surviving conditions that normally destroy Roman floor art within centuries. Researchers comparing Curion's mosaics to those at Pompeii Archaeological Park, Villa Romana del Casale, and Antioch Mosaic Museum notice something unusual. The mortar beneath Curion's mosaics appears exceptionally resistant to both humidity and microfracturing. Modern laboratory studies suggest the lime mixture may have undergone prolonged chemical curing, similar to advanced Roman marine concrete. Some samples contain microscopic crystalline bonding structures that strengthen over time when exposed to moisture. This has led to speculation that builders in Curion possessed localized material formulas now completely lost. Even more mysterious is how certain mosaic panels survived intact while surrounding stone walls collapsed entirely during the 365 AD earthquake. Some researchers suspect the flooring system itself distributed seismic stress differently from vertical masonry. In other words, the mosaics may not only have been decorative, they may also have been engineered for structural resilience. The destruction layer of 365 AD remains one of the most important earthquake records in archaeology. The earthquake likely originated near Crete and generated a massive tsunami across the eastern Mediterranean. Ancient historian Ammianus Marcellinus described entire coastlines being devastated. At Curion, evidence suggests the shaking intensity reached catastrophic levels. Columns snapped at their weakest stress points. Roof beams collapsed almost simultaneously. Human remains indicate many inhabitants died instantly, and entire residential sectors were abandoned afterward. Yet the destruction pattern remains inconsistent. Some areas were pulverized, while others survived surprisingly well only meters away. Modern geophysicists believe this may involve seismic wave amplification caused by cliff edge resonance, a phenomenon where certain geological formations magnify earthquake energy unpredictably. This effect has also been documented during modern earthquakes in Mexico City and parts of Turkey. But Curion presents one of the oldest known examples preserved archaeologically. Supplying water to a city built on unstable cliffs should have been nearly impossible, yet excavations uncovered a remarkably advanced hydraulic system, including ceramic pressure pipes, gravity-fed reservoirs, sediment control basins, and water distribution channels maintaining steady flow across uneven terrain. The precision of pipe alignment is especially impressive. Some ceramic sections fit together with millimeter-level accuracy despite being produced nearly 2,000 years ago. Even modern engineers acknowledge that maintaining hydraulic stability in seismic coastal terrain remains extremely difficult. What is astonishing is that parts of Curion's water infrastructure survived multiple earthquakes before the final destruction. Do you think Curion was abandoned because of fear, religion, or because its ancient engineering knowledge was permanently lost? Share your thoughts in the comments below. On a narrow stretch of the Mediterranean coast in southern Turkey, hidden between steep cliffs and crashing salt water, lie the ruins of Iyertate, also known today as Atap. At first glance, the city appears small compared to giants like Ephesus or Alexandria. But archaeologists who studied its submerged harbour, fractured sea walls, and cliffside engineering began noticing something strange. Many of its structures survived nearly 2,000 years in one of the most destructive environments possible: earthquakes, sea salt, humidity, and coastal erosion. The deeper researchers examined the site, the more Iyertate started to look less like an ordinary Roman port and more like a forgotten experiment in ancient engineering. The ruins were first systematically documented in the 19th and early 20th centuries during surveys of the Cilician coast. Located near modern Gazipaşa, on Turkey's Mediterranean shoreline, the city was built directly against unstable coastal rock formations. Modern geological studies show the region sits near active tectonic fault systems connected to the eastern Mediterranean seismic zone. In other words, Io tape was constructed in a place where large stone structures should have collapsed centuries ago, yet many sections still remain attached to the cliffs, while parts of its harbour continue to exist underwater. One of the greatest mysteries surrounds the ancient harbour itself. Large submerged blocks forming the harbour walls remain partially intact despite nearly 2,000 years of wave impact. Marine archaeologists noticed that some sections of mortar appear unusually resistant to seawater corrosion. This immediately drew comparisons to Roman marine concrete found at Pozzuoli and Caesarea. In Italy, Roman engineers used volcanic ash known as pozzolana, which chemically reacted with seawater to form durable minerals like aluminum tobamorite. These crystals actually strengthened the concrete over time instead of weakening it. But Io tape creates a major problem for that theory. The region lacks the massive volcanic ash deposits found near Naples, yet mineral traces inside some harbour mortar samples suggest similar long-term crystallization reactions may have occurred. This has led researchers to suspect that engineers at Io tape either imported volcanic materials through Mediterranean trade routes or developed a localized formula using coastal minerals and kiln ash. If true, it would mean advanced marine concrete technology spread much farther across the Roman world than historians once believed. The harbour also reveals another unexplained feature. Some of the giant coastal blocks were positioned with small gaps rather than tightly compressed joints. At first, this looked like poor workmanship, but structural engineers studying earthquake-resistant architecture noticed the spacing may have served a purpose. Tiny flexible joints can absorb seismic vibration by allowing stone sections to shift slightly instead of cracking under pressure. Similar principles appear in Inca masonry at Machu Picchu and Sacsayhuaman in Peru, where polygonal stones survived repeated earthquakes without modern cement. The comparison becomes even stranger when measurements are examined. In some sections of Io tape's harbour walls, displacement damage appears far lower than expected for structures repeatedly exposed to seismic activity over centuries. Researchers still debate whether this was intentional engineering or simply an accidental consequence of Roman construction methods. Either explanation raises uncomfortable questions about how sophisticated ancient seismic knowledge may actually have been. Water management at Io tape presents another mystery. Fresh water was critical because the city stood directly beside saltwater cliffs. Archaeologists discovered carved channels cut into coastal rock leading from elevated inland zones toward the settlement. What shocked surveyors was the consistency of the channel gradients. In some preserved stretches, the slope varies by only a few millimeters per meter, a level of precision comparable to famous Roman aqueducts like the Pont du Gard in France. Maintaining such accuracy across uneven cliff terrain without laser equipment or modern optics should have been extremely difficult. Roman engineers are believed to have used water leveling systems, plumb lines, and astronomical alignment techniques. But at Io tape, the channels follow dangerous rocky contours where even small errors could disrupt water flow entirely. Some sections appear carved directly into near-vertical stone surfaces, exposed to sea winds and erosion. The engineering challenge resembles systems later seen in Petra, where Nabatean engineers controlled water flow through desert cliffs with astonishing precision. Even more mysterious is how buildings at Io tape were anchored onto unstable slopes. Modern coastal engineering often requires deep, reinforced foundations to stabilize heavy structures near eroding cliffs. Yet many structures at Iotape were built directly onto bedrock with relatively shallow foundations. Geological analysis suggests ancient builders may have intentionally integrated structures into natural rock stress lines rather than fighting against them. Several cliffside buildings also contain unusually flat stone-cut surfaces beneath the foundations. The cuts are remarkably level despite the uneven terrain. Similar precision stone preparation has been identified in Petra, Baalbek, and parts of ancient Egypt. While none of these sites necessarily prove the existence of lost technology, they demonstrate that ancient stoneworking precision was often far more advanced than public imagination assumes. Another unexplained aspect involves moisture control. Coastal humidity and salt should have rapidly destroyed interior floors and wall systems. Yet remnants of layered flooring systems suggest Iotape's builders used multi-level drainage and airflow techniques beneath some structures. Certain bathhouse remains show evidence of subfloor cavities designed to reduce trapped moisture. These systems resemble passive ventilation concepts used in modern humid climate architecture. Researchers comparing Roman bath complexes discovered similarities to Hipparcost-inspired airflow systems, although adapted to coastal conditions rather than heating. In practical terms, Iotape may have developed hybrid architectural solutions specifically for surviving Mediterranean humidity and salt exposure. This becomes especially surprising considering the city was relatively small compared to major imperial centers. But perhaps the greatest mystery is why parts of the city are now underwater. Marine surveys show portions of the harbour and coastal structures sit several meters below modern sea level. Scientists continue debating whether this resulted primarily from tectonic subsidence, earthquakes, rising sea levels, or a combination of all three. Sediment analysis suggests slow geological sinking may have occurred over centuries. If so, Iotape provides rare evidence of how ancient cities gradually adapted to environmental collapse long before modern climate discussions existed. Some archaeologists believe entire sections of the harbour remain buried beneath underwater sediment. Sonar scans along sections of the coast hint at additional submerged structures still unexplored. Each new survey raises the possibility that critical parts of Iotape's engineering systems remain hidden beneath the Mediterranean floor. What do you think explains the engineering precision and durability of Iotape? Advanced ancient knowledge, lost techniques, or something else we still haven't uncovered? Share your thoughts in the comments below. Far above the plains of Argolis in northeastern Greece, massive stone walls still rise from a rocky hill that has survived more than 3,000 years of earthquakes, invasions, collapse, and abandonment. The Acropolis of Medea was once one of the most heavily fortified strongholds of the Mycenaean civilization, built during the Late Bronze Age around the 14th and 13th centuries BCE. Yet compared to nearby Mycenae or Tiryns, Medea remained strangely overlooked for centuries. That changed when systematic excavations in the 20th century began revealing a fortress filled with engineering mysteries that modern archaeologists still struggle to fully explain. The site lies roughly 15 kilometers east of Mycenae in the Argolis region of Greece. Excavations led by Greek and Swedish archaeologists uncovered enormous fortification walls, underground storage systems, advanced drainage networks, workshops, and evidence of sudden destruction around 1200 BCE. During the catastrophic collapse of Bronze Age civilizations across the Eastern Mediterranean. But what shocked researchers most was not simply the scale of the fortress, it was the level of engineering sophistication hidden inside structures built more than 1,000 years before classical Greece even existed. The most famous mystery surrounding Medea is its gigantic cyclopean fortification walls. These walls were constructed using limestone boulders so enormous that later Greeks believed only mythical cyclopes could have lifted them. Some stones weigh between 5 and 10 tons, while sections of wall still stand more than 7 meters high and several meters thick. Unlike Roman masonry, the stones were not shaped into perfect blocks. Instead, irregular massive rocks were fitted together with extraordinary precision, often without mortar. Even after millennia of earthquakes, many sections remain stable. The engineering challenge becomes even more disturbing when considering Bronze Age technology. Archaeologists have found no evidence of iron cranes, advanced pulleys, or mechanical lifting systems capable of transporting thousands of tons of stone uphill. Experimental archaeologists estimate that moving just one 10-ton block using wooden sledges and ropes would require dozens of workers, coordinated force distribution, and carefully engineered ramps. Yet, Medea's walls were built on steep terrain under highly organized planning. Similar Cyclopean construction also appears at Mycenae and Tiryns, but some researchers argue Medea's terrain would have made transportation even more difficult than at those sites. Modern structural engineers studying the walls discovered another anomaly. The stones are not stacked vertically in a simple straight pattern. Many layers lean slightly inward, creating a form of primitive seismic stabilization. The Argolis region sits near active tectonic fault systems and has experienced destructive earthquakes for thousands of years. Geological studies suggest a major earthquake likely struck Medea around the late 13th century BCE, damaging sections of the fortress. Yet large portions survived. Some engineers believe the irregular interlocking stones distributed seismic energy more effectively than rigid uniform walls. Similar principles appear in certain Inca constructions in Peru nearly 2,000 years later, where polygonal stones helped structures survive earthquakes. The question is whether the Mycenaeans intentionally understood seismic behavior or accidentally discovered earthquake-resistant architecture through generations of trial and error. Inside the fortress, excavations uncovered complex storage facilities that reveal another technological mystery. Large underground rooms stored olive oil, grain, wine, and military supplies, essential for sustaining the population during siege conditions. These chambers maintained surprisingly stable internal temperatures, despite the Mediterranean climate outside. Researchers studying airflow patterns found that narrow ventilation passages may have helped regulate humidity and heat naturally. Some archaeologists compare this to passive climate control systems, seen much later in Persian desert architecture or Roman storage engineering. The sheer amount of stored goods also suggests an advanced, centralized administration capable of collecting, measuring, and redistributing agricultural resources on a regional scale. Fragments of Linear B tablets found in the wider Mycenaean world support this theory. Linear B, an early Greek administrative script, recorded inventories, taxation, livestock, bronze allocation, and labor organization. Although few tablets survived directly at Medea itself, the fortress likely operated within the same bureaucratic network as Mycenae and Pylos. This creates a disturbing implication. The Mycenaean kingdoms may have been far more economically interconnected than previously believed, functioning almost like an early proto-state system centuries before classical empires emerged. Another mystery lies beneath the floors and pathways of the Acropolis. Archaeologists discovered sophisticated drainage channels designed to move rainwater away from critical structures. The channels were carefully angled to maintain water flow while minimizing erosion against the foundations. Some stone surfaces even appear coated with materials that improved water resistance, though the exact composition remains debated. Similar hydraulic sophistication existed at Minoan Crete, particularly at Knossos, where drainage systems and plumbing amazed modern engineers. But Medea was primarily a military fortress, making its advanced water management especially unusual. The eastern gate of Medea reveals an equally chilling level of military intelligence. Rather than allowing direct access into the citadel, the entrance forced attackers through narrow, confined passageways bordered by thick defensive walls. Invading soldiers would have exposed their unshielded right side while advancing, creating a deadly kill zone for defenders positioned above. Medieval castles later adopted comparable defensive choke points, yet Medea achieved this tactical architecture over 2,000 years earlier. Some military historians argue that Mycenaean warfare may have involved far more organized siege tactics than traditionally imagined. Evidence of industrial activity inside the fortress adds another layer of mystery. Excavations uncovered pottery workshops, evidence of bronze working, and signs of large-scale production. Bronze Age metallurgy required extremely high temperatures, often exceeding 1,000 degrees Celsius, to properly smelt copper alloys. Achieving such heat consistently demanded carefully controlled furnaces, airflow systems, and fuel management. Scientists studying slag remains from Mycenaean sites concluded that Bronze Age metallurgists possessed a surprisingly advanced practical understanding of thermal control despite lacking modern chemistry. Some researchers even compare the organizational complexity of Bronze Age bronze production to early industrial systems. Then came the collapse. Around 1200 BCE, major civilizations across the eastern Mediterranean began falling almost simultaneously. The Hittite Empire disappeared, trade networks failed, Egyptian records described mysterious sea peoples attacking coastal regions. Mycenaean centers, including Medea, Mycenae, and Pylos, suffered destruction through fire, warfare, or earthquakes. At Medea, archaeologists found collapsed walls, burned structures, and signs of sudden chaos. Yet unlike some cities that vanished immediately, Medea shows evidence of partial rebuilding after the disaster. This suggests survivors briefly attempted to restore the fortress before abandoning it permanently. Why the Mycenaean world collapse remains one of archaeology's greatest unsolved mysteries. Some scientists point toward climate change and prolonged droughts affecting agriculture across the eastern Mediterranean. Pollen studies and sediment cores indicate periods of severe environmental stress during the late Bronze Age. Others argue that interconnected trade systems became too fragile, causing economic collapse after disruptions in bronze supply routes. Bronze depended on imported tin, a rare resource often transported across enormous distances. Once trade failed, weapons production, agriculture, and political stability may have rapidly deteriorated. But Medea raises a deeper question. How advanced was Mycenaean engineering before the collapse erased much of its knowledge? Unlike Egypt or Rome, the Mycenaeans left relatively few surviving written records explaining how their structures were built. Many technologies appear suddenly in the archaeological record, then disappear after the Bronze Age collapse. For centuries afterward, Greece entered a period often called the Greek Dark Age. Monumental architecture declined, literacy vanished temporarily, large centralized construction projects almost disappeared. It was as if an entire system of engineering knowledge had fractured and been lost. Tiryns rises from the rocky plains of the Argolis region in Greece like the remains of something that should not have existed in the Bronze Age. Just a few kilometers from Nafplio, archaeologists uncovered a fortress city whose walls were so massive that ancient Greeks themselves refused to believe ordinary humans had built them. They called the structure Cyclopean, claiming only the mythical Cyclopes, giant one-eyed beings, could have moved stones of such impossible size. Modern archaeology officially dates Tiryns to around the 13th century BCE during the height of Mycenaean civilization. Yet even with today's engineering knowledge, many of its construction methods remain only partially explained. The site was systematically excavated in the late 19th century by Heinrich Schliemann and Wilhelm Dorpfeld, after Schliemann's discoveries at Messini transformed the study of Bronze Age Greece. What they uncovered beneath layers of clapped stone was not a primitive hill fort, but a heavily engineered military citadel with advanced defensive planning, hydraulic systems, internal galleries, and structural techniques capable of surviving more than 3,000 years of earthquakes. Some archaeologists now describe Tiryns as one of the earliest examples of large-scale integrated military engineering in Europe. The first mystery begins with the walls themselves. Certain limestone blocks used in the outer fortifications weigh between 10 and 20 tons, while a few may exceed 30 tons. The walls reach nearly 13 meters in height, and in some places are over 8 meters thick. Unlike later Roman masonry, many stones at Tiryns were only partially shaped, then fitted together with remarkable stability without thick mortar layers. The problem is technological. Around 1200 BCE, the Messenians possessed bronze tools, not hardened steel. There is no evidence of advanced cranes, iron reinforcement systems, or complex pulley machinery capable of lifting such enormous masses efficiently. Even transporting stones of this scale over uneven terrain would have required extraordinary organization. Comparisons with other Bronze Age sites make Tiryns even more unusual. Massive stone architecture existed elsewhere, including the Hittite capital of Hattusa and certain Egyptian temple complexes. But Tiryns differs in the density and scale of its defensive engineering. Egyptian monuments focus primarily on ceremonial construction, while Tiryns appears optimized for survival during siege warfare and seismic instability. Some engineers studying the site argue that the irregular shapes of the blocks were not simply crude workmanship, but intentionally designed to distribute stress and reduce catastrophic collapse during earthquakes. That theory became more important after geological studies revealed how seismically active the region is. Southern Greece sits near multiple tectonic fault systems, and major earthquakes have repeatedly devastated ancient settlements there. Yet large portions of Tiryns still stand after more than 3 millennia. Modern structural engineers examining Cyclopean masonry notice something surprising. The rough stone interfaces create frictional resistance that allows energy dissipation during ground movement. In simple terms, the walls can shift slightly under stress without immediately failing. This resembles certain principles used in modern earthquake-resistant construction, where flexibility is sometimes more important than rigid perfection. Unlike the tightly cut polygonal masonry later seen in parts of the Inca world or at some Roman structures, Tiryns balances irregularity with weight distribution. Some researchers compare this to primitive seismic damping. While there is no evidence the Mycenaeans understood plate tectonics, they may have developed practical engineering knowledge through repeated exposure to earthquakes over generations. The idea that a Bronze Age civilization unintentionally discovered principles similar to anti-seismic engineering remains one of the most debated aspects of the fortress. Another mystery lies hidden inside the walls. Tiryns contains long internal galleries built directly into the fortifications themselves. These corridors use corbel vault construction, where successive stone layers gradually project inward until they meet at the top. The technique appears simple, but it creates complex load distribution problems. If calculations are even slightly wrong, thousands of tons of pressure can collapse the entire passageway. Some of these galleries stretch for dozens of meters and may have functioned as protected troop corridors, storage chambers, or emergency movement routes during attacks. Their existence suggests that Tiryns was not merely a walled city, but a deeply planned military structure. The engineering sophistication is especially striking because these vault systems predate the famous arches of Rome by many centuries. Roman arches distribute weight through compression geometry, but Tiryns achieved long-lasting stability using a more primitive yet surprisingly durable alternative. The internal design of the citadel also reveals unusual strategic thinking. Instead of constructing the fortress on flat terrain, the Mycenaeans built directly onto a rocky limestone hill. This dramatically increased foundational stability while improving visibility across the Argolis plain. Modern geotechnical studies suggest that the underlying bedrock reduced long-term settlement and structural sinking. Many Bronze Age cities built on softer sediment eventually suffered catastrophic instability, but Tiryns remained unusually resilient. Water management at the site creates another layer of mystery. Excavations revealed sophisticated drainage channels beneath palace floors and defensive sections. Stone-lined conduits directed rainwater away from critical structures using carefully calculated gradients. Several channels still function if exposed to flowing water today. For a civilization operating more than 3,000 years ago, this level of hydraulic planning is remarkable. Comparable drainage systems are often associated with much later Roman urban engineering, yet Tiryns demonstrates that advanced water control already existed in Mycenaean Greece centuries earlier. Archaeologists also found evidence suggesting the citadel once supported a highly organized administrative economy. The palace complex likely coordinated food storage, military logistics, craft production, and regional trade. But this creates another unanswered question. How did a Bronze Age kingdom manage labor on such a scale? Constructing Tiryns may have required thousands of workers over decades, including quarry specialists, transport crews, engineers, planners, and administrators capable of maintaining food supplies and coordination. The surviving Linear B tablets from the Mycenaean world provide only fragmented information about this administrative system. They record inventories, livestock counts, and offerings, but reveal little about how megastructures like Tiryns were actually designed and constructed. The absence of detailed engineering records creates what some historians call a knowledge gap in Bronze Age archaeology. The civilization clearly possessed abilities far beyond what its surviving documents explain. The collapse of the Mycenaean world around 1200 BCE deepens the mystery further. Many major centers across the eastern Mediterranean fell during the late Bronze Age collapse, including Hittite territories and numerous Levantine cities. Tiryns survived longer than many neighboring sites, but eventually declined as regional systems broke apart. Some evidence suggests earthquakes contributed to damage at the fortress, while other scholars point toward warfare, economic collapse, or internal instability. What remains astonishing is that despite destruction, invasion, weathering, and repeated seismic activity, major portions of the fortress still endure. What do you think explains Tiryns' advanced engineering, lost knowledge, gradual experimentation, or something we still don't understand? Leave your thoughts in the comments below.